Look up at the night sky, whether you're in a city washed in the orange glow of streetlights, or far out in the countryside where the darkness is absolute. That sight is one of the most ancient experiences shared by humanity. For millennia, we have gazed upon those points of light, charting the wanderers among the fixed stars, telling stories of gods and heroes written in constellations. Yet for all that history, there is a question that whispers from the darkness, a question that has only grown deeper and more profound with our modern understanding. Why does the universe, in all its staggering vastness, look like this? Why do galaxies spin in majestic spirals? Why do nebulae glow with such impossible colors? And why does the fabric of spacetime itself appear to be arranged in a cosmic web of unimaginable scale? This isn't just a question about what we see, it's a question about why we see it at all. The universe could have been a formless, dark, and empty void. Instead, it is a riot of structure, light, and complexity, and the reason for that is one of the greatest stories ever told. This journey takes us to the very edge of what is known and what is still a profound mystery. We will explore how the laws of physics, written in the first fleeting moments after the Big Bang, set the stage for everything that was to come. We will see how the tiniest quantum fluctuations were stretched to cosmic proportions, becoming the seeds for galaxies, stars, and ultimately for us. It's a story that connects the infinitesimally small to the astronomically large, a narrative written in the light of quasars and the whisper of the cosmic microwave background radiation. The appearance of our universe is not an accident. It is a direct consequence of a handful of fundamental constants and forces working in concert over nearly 14 billion years. Change one of those numbers even by a tiny amount, and the cosmos would be unrecognizable, a dark, lifeless emptiness, or perhaps a chaotic fireball. So, as we embark on this exploration, we are not just looking at pretty pictures from powerful telescopes. We are reading the history of existence itself, deciphering the clues left behind in the distribution of galaxies and the afterglow of creation. This video is an invitation to step back and consider the canvas of the cosmos. We will travel from the quantum foam that birthed reality to the vast cosmic web that defines the largest structures in existence, all in an effort to answer that simple yet infinitely deep question. Why does the universe look the way it does? The answer is a tapestry woven from dark matter, dark energy, gravity, and light. And it is a story that is still being written, with every new observation adding another thread to the grand design. But to even begin deciphering that story, we first have to understand the very nature of our view. When we peer into the depths of space with our most powerful telescopes, we are not looking out at an infinite, unchanging universe. We are looking back in time. Every photon of light that strikes a telescope mirror is a messenger from the past, and it has been traveling across the cosmos for millions, even billions of years. This simple fact leads us to one of the most fundamental and humbling concepts in all of cosmology, the idea of the observable universe. Think of it like this: you are standing in the center of an immense foggy landscape. The fog represents the early, dense state of the universe. As light travels toward you, the fog gradually clears, but you can only see the objects whose light has had enough time to reach you through that clearing fog. The sphere of space containing all those objects, everything whose light has reached us since the beginning, that is our observable universe. Its boundary is what we call the cosmic horizon. This horizon isn't a physical wall you could bump into. It's a limit set by the finite speed of light and the finite age of the cosmos. Since the universe is about 13.8 billion years old, you might think we should be able to see objects that are 13.8 billion light years away. But the story is more fascinating and complex because the fabric of space itself has been expanding all this time. The most distant light we can detect is the cosmic microwave background radiation, the afterglow of the Big Bang, which has been traveling for nearly the entire age of the universe. Yet, because space has stretched tremendously during that light's journey, the places where that radiation originated are now actually about 46 billion light-years away from us. So, our observable universe is a sphere with a radius of 46 billion light-years, centered from our perspective right here on Earth. And this is a crucial point. Every observer in the universe has their own observable sphere, their own cosmic horizon. An intelligent being on a planet in the Andromeda galaxy would be the center of their own observable universe, with a view that partially overlaps with ours but also includes regions forever hidden from our sight. This leads us to the profound and perhaps unsettling implication. What lies beyond our cosmic horizon? The most honest answer, based on our current understanding of physics, is that we can never know. The space beyond that 46 billion light-year limit is not just empty, it is fundamentally inaccessible. Any information from those regions, any light, any gravitational wave, any form of signal, has not had enough time to reach us since the universe began. Even if the greater universe is infinite in extent, our ability to observe it is forever confined to this finite, horizon-bound bubble. The universe beyond the horizon is causally disconnected from us. Events happening there cannot affect us, and we cannot affect them. It is a realm of permanent mystery. This concept shatters any naive idea that we can see the entire universe. We are limited to a single chapter of a story whose full length we may never comprehend. A chapter written in the light that has finally, after an epic journey, managed to find its way to our eyes. And so, if our observable universe is a sphere of history defined by the light that has reached us, then light itself becomes the central character in our cosmic story. It is the universe's primary messenger, the only thing that can cross the unimaginable voids between stars and galaxies to whisper their secrets directly to us. But what we perceive with our eyes as visible light, the beautiful colors of nebulae and the steady glow of stars, is just one tiny fragment of a much grander conversation. Light is actually a wave traveling through the fabric of space-time, and it comes in a vast spectrum of energies and wavelengths, a full orchestra of information where our eyes are only tuned to hear a single, quiet instrument. This entire range is known as the electromagnetic spectrum. At one end, you have long, lazy radio waves, which can be as long as buildings or even entire continents. These are the waves that carry our radio stations and television signals, but in astronomy, they allow us to map the cold, dark hydrogen gas between stars and see the faint, ancient glow of the universe's infancy. Then there are microwaves, famous for heating our food, but cosmologically vital for capturing the cosmic microwave background, that pristine afterglow from a time when the universe was a hot, dense plasma. Moving to shorter wavelengths, we encounter infrared light, which we feel as heat. This is the key to piercing through cosmic dust clouds that block visible light, revealing the nurseries where new stars are being born, hidden from our ordinary sight. Further along, we have the narrow sliver of the spectrum our eyes evolved to see, visible light. This is where stars like our sun pour out most of their energy, and it gives us the iconic, breathtaking images of galaxies and nebulae. But the spectrum continues into higher energies. Ultraviolet light, which causes sunburns, reveals the hottest, most energetic young stars. X-rays allow us to detect the violent surroundings of black holes and the superheated gas in galaxy clusters. And at the far end of the spectrum are gamma rays, the most energetic photons of all, born from the most cataclysmic events in the universe, like colliding neutron stars and supernova explosions. Each of these bands of light tells a different part of the cosmic story, and to get the full picture, we cannot rely on our eyes alone. We need technological proxies, extraordinary eyes that can see what we cannot. This is where our great observatories come in, each designed to listen to a specific part of this cosmic symphony. The Hubble Space Telescope, for decades, has been our master interpreter of visible and ultraviolet light, delivering images that have defined our generation's understanding of the cosmos, the pillars of creation, the deep-field galaxies, the elegant whirl of distant spirals. But Hubble's view, as profound as it is, was like hearing only the string section of an orchestra. To hear the full composition, we needed to listen to the deeper notes. The James Webb Space Telescope is our infrared maestro. By observing the universe in infrared light, Webb can peer through obscuring dust to witness the birth of the first stars and galaxies. And because of the expansion of the universe, the light from these most ancient objects has been stretched or redshifted from visible light into the infrared part of the spectrum. Webb is quite literally a time machine, capturing light that has been traveling for over 13 billion years, allowing us to see the universe's first chapters. But the conversation doesn't stop there. Observatories like the Chandra X-ray Observatory show us the universe in a state of extreme violence and energy, mapping the ghostly halos of multimillion-degree gas that envelop entire galaxies. Radio telescopes, whether single dishes like the Arecibo Observatory or vast arrays like the Very Large Array, stitch together maps of the cosmic web's underlying structure by detecting the faint radio signals from distant hydrogen. By combining all these different views, the radio, the infrared, the visible, the X-ray, we are no longer just looking at pictures. We are assembling a multi-dimensional portrait of the cosmos. We see not only what something looks like, but we can infer its temperature, its composition, its motion, and its history. A dark cloud in a visible light image glows with the heat of infant stars in an infrared view. A seemingly ordinary star in an optical telescope is revealed to be a powerful X-ray source, hinting at an invisible companion, a black hole or neutron star pulling material from it. This symphony of light transforms our understanding from a passive observation into an active interrogation of the universe. We are not just waiting for messages to arrive, we are building instruments to ask specific questions across the entire electromagnetic spectrum. Every wavelength we unlock is like learning a new language, allowing us to read another chapter of the cosmic story written in the sky, a story that began with a flash of light and continues to reveal itself across the vast spectrum of existence. This idea that light takes time to reach us transforms every dot of light in the night sky into a tiny time capsule. Consider our closest large galactic neighbor, the Andromeda Galaxy. When you find it with binoculars or a small telescope, that faint, fuzzy patch of light is not a picture of what Andromeda looks like today. You are seeing it as it was 2.5 million years ago. The photons striking your retina began their journey at a time when early humans were just beginning to walk the Earth. If, by some impossible means, we could see Andromeda as it is at this very moment, we might witness events that unfolded long after our own species learned to use tools and harness fire. Every single celestial object we observe carries its own timestamp, a direct measure of its distance from us written in the travel time of its light. This principle scales up to truly mind-bending proportions. The bright star Sirius, the brightest star in our sky, appears to us as it was about 8.6 years ago. The light from the magnificent Orion Nebula, a stellar nursery, is roughly 1,300 years old, meaning we see it as it was around the time of the fall of the Western Roman Empire. Push further out, and the light from the center of our own Milky Way galaxy has been traveling for about 27,000 years, a time when the last ice age was still gripping the planet. With each step deeper into space, we take a greater step back in time. Our most powerful telescopes act as true time machines. The Hubble Space Telescope's famous deep field image, which revealed thousands of galaxies in a patch of sky once thought empty, captured light that had been traveling for over 13 billion years. We are not just looking across space, we are witnessing these galaxies in their infancy, seeing the universe as it was when it was less than 1 billion years old. This incredible ability to peer into the past is the single most powerful tool in a cosmologist's arsenal. It means the history of the universe is not a theoretical concept to be modeled on a supercomputer. It is literally written across the sky, available for us to observe directly. By looking at galaxies at different distances and therefore from different epochs, we can watch the universe evolve. We can see young, chaotic galaxies from the early universe actively colliding and forming stars at a ferocious rate. As we look at closer and therefore more recent galaxies, we can observe how they settled into the majestic, orderly spirals and ellipticals we see in our cosmic neighborhood today. This is like having a photo album of the cosmos, with snapshots arranged in chronological order simply by their distance from us. There is, however, a fundamental limit to our view, a point beyond which we cannot see. This limit is not a barrier in space, but a wall in time. In the very early universe, before the first stars and galaxies ignited, the cosmos was a hot, dense, opaque fog of plasma and energy. Light particles or photons could not travel freely. They were constantly bouncing off free electrons like light trying to shine through thick, dense fog. About 380,000 years after the Big Bang, the universe had expanded and cooled enough for electrons to combine with protons and form the first neutral atoms. In this moment, often called recombination, the fog suddenly lifted. The photons once trapped were finally set free to travel across the universe. This first light, now stretched and cooled by the expansion of the universe over billions of years, is what we detect today as the cosmic microwave background radiation. It is the oldest light we can possibly observe, the final scattering surface that forms the ultimate boundary of our observable universe. We cannot see any further back in time because for the first 380,000 years, the universe was simply not transparent to light. This ability to look back in time, to see the universe in its youth, presents us with one of the most startling and transformative discoveries in the history of science. It wasn't enough to simply observe that the universe was vast and ancient. The real revolution came when we began to measure how it was moving. In the early 20th century, the prevailing view was of a static, unchanging cosmos, an eternal island of stars. But this comfortable idea was about to be shattered by a simple observation of light. Astronomers like Vesto Slipher began to notice something peculiar when they analyzed the light from distant spiral nebulae, which we now know are other galaxies. The dark lines in their spectra, the unique fingerprints of chemical elements like hydrogen and calcium, were not where they were supposed to be. They were systematically shifted toward the red end of the spectrum. This phenomenon, called redshift, was the key that unlocked the true nature of the cosmos. We're all familiar with a similar effect with sound waves, known as the Doppler effect. When an ambulance speeds toward you, its siren sounds higher in pitch because the sound waves are compressed, shortening their wavelength. As it passes and moves away, the pitch drops because the waves are stretched, lengthening their wavelength. Light behaves in a fundamentally similar way. If a galaxy is moving toward us, its light waves are compressed, shifting its spectral lines toward the blue end, a blue shift. But what Slipher and later Edwin Hubble found was the opposite. Nearly every galaxy showed a redshift. They were all moving away from us. Hubble's genius was in combining these redshift measurements with estimates of the distances to these galaxies. What he found in 1929 was staggering. The farther away a galaxy was, the greater its redshift. In other words, the more distant the galaxy, the faster it was receding from us. This relationship, now known as Hubble's law, pointed to one inescapable conclusion. The universe itself is expanding. It's not that galaxies are simply flying apart through a static, pre-existing space like shrapnel from an explosion. Instead, the very fabric of space between the galaxies is stretching. Think of the universe as a loaf of raisin bread rising in the oven. Each raisin represents a galaxy. As the dough expands, every raisin moves away from every other raisin. From the perspective of any single raisin, all the others are receding, and the ones farther away appear to move faster because there's more expanding dough between them. This is precisely what we observe from our galactic raisin. This expansion of space has a direct and profound effect on the light traveling through it. As a photon of light journeys for millions or billions of years across the cosmos, the space it traverses is continually stretching. This stretches the photon's wavelength itself, making it longer. Since red light has the longest wavelengths we can see, this stretching causes the light to become redder, hence the term cosmological redshift. The degree of redshift, therefore, becomes a direct measure of how much the universe has expanded since that light was emitted. A galaxy with a small redshift is relatively close. Its light hasn't traveled through a vast amount of expanding space. But a galaxy with a tremendous redshift is incredibly far away, and its light has been stretched over an epic journey, telling us it was emitted when the universe was far more compact than it is today. This discovery fundamentally changed our understanding of everything. An expanding universe implies that if we could run the film of cosmic history backward, everything would get closer and closer together. All the matter and energy we see today will be compressed into an increasingly hot, dense state. This logic leads directly to the concept of the Big Bang, a definite beginning to the universe as we know it from a singular, hot, dense origin. Furthermore, by carefully measuring the Hubble constant, the rate of the universe's expansion, we can actually calculate the age of the universe. It's like figuring out how long a car journey has taken by knowing its speed and distance. We work backward from the current expansion rate to estimate when the cosmic journey began, arriving at that figure of 13.8 billion years. The expansion of space, revealed by the redshift of distant galaxies, is the central plot of our cosmic story. It's the engine that drives the evolution of the universe, cooling the primordial plasma, allowing atoms to form and setting the stage for the birth of galaxies. It tells us that the cosmos is not static and eternal, but dynamic and evolving, with a past, a present, and a future that is still being written by this relentless, invisible stretching of the very vacuum of space itself. For decades after Hubble's monumental discovery, scientists assumed that while the universe was indeed expanding, the mutual gravitational pull of all the matter within it must be putting the brakes on that expansion. It was a logical assumption. Gravity is an attractive force, and with so much mass scattered across the cosmos, everything should be gradually slowing down. The big question for cosmologists was whether there was enough matter to eventually halt the expansion entirely, leading to a big crunch, or if the universe would just keep expanding forever at a steadily decreasing rate. This was one of the most profound puzzles of 20th century science, and answering it required looking deeper into space and further back in time than ever before. The key was to measure the expansion rate not just in the recent universe, but billions of years ago, to see how it had changed over cosmic history. The tool for this cosmic archaeology turned out to be a specific kind of stellar explosion, a standard candle of incredible brightness known as a Type I supernova. These are not the explosions of massive stars, but rather of white dwarfs, the dense, Earth-sized cores of dead sun-like stars. When a white dwarf in a binary system siphons off enough material from its companion to reach a critical mass, it undergoes a thermonuclear explosion that is so uniform and so phenomenally bright that it can outshine an entire galaxy. This consistency in their peak brightness makes them perfect for measuring vast distances. By observing how bright a distant supernova appears to us and knowing its intrinsic brightness, astronomers can calculate precisely how far away it is. And by measuring its redshift, they can determine how much the universe has expanded since the moment the star exploded. In the late 1990s, two independent teams of astronomers were using these supernovae to measure the deceleration of the universe. They expected to see that the expansion was slower in the past than it is today, meaning that the most distant supernova would be slightly brighter than anticipated for their redshift because the universe hadn't expanded as much back then. But the data revealed the exact opposite. the incredibly distant supernova whose light had been traveling for billions of years were significantly fainter than their redshifts predicted. This could only mean one astonishing thing: the universe was expanding more slowly in the past than it is now. The expansion wasn't slowing down at all, it was speeding up. Some mysterious, repulsive force was acting against gravity, pushing galaxies apart with ever-increasing vigor. This discovery was so shocking and counterintuitive that the researchers spent years checking and rechecking for potential errors, like intergalactic dust dimming the light. But the evidence was conclusive. In 2011, the leaders of these teams were awarded the Nobel Prize in Physics for a finding that fundamentally overturned our understanding of cosmic destiny. This mysterious agent of acceleration was dubbed dark energy. The name itself is a testament to our ignorance. We know it exists by its dramatic effect on the cosmos, but we have no idea what it actually is. The simplest and currently most favored explanation is that dark energy is an inherent property of space itself. Empty space, according to quantum physics, is not truly empty. It is a seething foam of virtual particles popping in and out of existence. This vacuum energy could exert a negative pressure that causes space to expand. The more space there is, the more of this energy exists, leading to a self-reinforcing cycle of acceleration. This idea was actually first proposed by Albert Einstein himself as his cosmological constant, a term he added to his equations of general relativity to achieve a static universe, which he later called his greatest blunder. It turns out his blunder may have been prematurely judged. The cosmological constant is a prime candidate for the dark energy driving the acceleration. The implications of dark energy are staggering. Measurements from supernova, combined with data from the cosmic microwave background and the large-scale structure of the universe, now tell us that dark energy makes up about 68% of the total energy density of the cosmos. The matter we are familiar with, all the stars, planets, gas, and dust, comprises a mere 5%. The remaining 27% is the equally mysterious dark matter. This means that the universe we see, the glorious tapestry of galaxies and nebulae that fills our telescopes, is just a tiny fraction of what's actually out there. The dominant components of the cosmos are completely invisible to us, their presence inferred only through their gravitational and repulsive influence on the evolution of everything. This invisible hand of dark energy has a profound influence on the large-scale structure of the universe. In the past, when the universe was smaller and denser, gravity was the dominant force, pulling matter together to form galaxies and the vast filamentary cosmic web. But as the universe has expanded and become more diffuse, the effect of dark energy has grown stronger. It now acts as a kind of cosmic repulsor, working against gravity's tendency to pull things together. On the scale of individual galaxies and even galaxy clusters, gravity still holds sway. But on the very largest scales, dark energy is now in control, accelerating the expansion and driving galaxy clusters ever further apart. In the far future, this acceleration promises a lonely and increasingly dark cosmos. Billions of years from now, any civilizations that arise will look up at a sky devoid of other galaxies, as all but the closest neighbors will have been accelerated beyond our cosmic horizon. The universe will become a much darker, emptier place, a fate dictated by this enigmatic force we are only just beginning to comprehend. So if dark energy is the force pushing the cosmos apart on the grandest scales, what is it that provided the initial pull, the gravitational blueprint that allowed the universe to become structured in the first place? The story of cosmic structure leads us directly to one of the most enduring and profound mysteries in all of physics, the enigma of dark matter. The evidence for this invisible component of the universe is not based on what we can see, but on how the things we can see are moving. The first major clue emerged from the study of something seemingly simple, the way galaxies spin. Our own Milky Way, like other spiral galaxies, rotates like a giant cosmic pinwheel. Based on Newton's and Einstein's laws of gravity, we can make a straightforward prediction. The stars and gas clouds in a galaxy should orbit the center at speeds that decrease with distance, much like the planets in our solar system. Mercury, close to the Sun's immense gravity, moves very quickly, while Neptune, far out in the cold depths, plods along slowly. But in the 1970s, astronomer Vera Rubin, using precise measurements of the rotation speeds of stars and gas in the Andromeda Galaxy, found something that defied this expectation. The stars far from the galactic center were not moving more slowly. They were orbiting at nearly the same high speed as the stars closer in. This was like discovering that all the planets in our solar system, from Mercury to Neptune, were whipping around the Sun at the same incredible velocity. For this to be possible, the gravitational pull holding these outer stars in their fast orbits had to be much, much stronger than the gravity from the visible matter alone could provide. The only explanation was that galaxies are embedded within vast, massive halos of some unseen material, a form of matter that does not emit, absorb, or reflect any light. This invisible mass provides the extra gravitational glue needed to explain the unexpectedly high rotation speeds. Without it, the outer regions of galaxies would simply fly apart. This discovery of flat rotation curves was the first solid, incontrovertible evidence for dark matter, but it was far from the last. Another line of evidence comes from looking at the very largest structures in the universe, galaxy clusters. These are immense gatherings of hundreds or even thousands of galaxies bound together by gravity. We can estimate the total mass of a cluster in two ways. First, we can add up the mass of all the visible components, the stars in all the galaxies and the hot gas that glows in X-rays between them. Second, we can measure the cluster's total gravity by observing how it bends light from more distant galaxies behind it, an effect predicted by Einstein called gravitational lensing. The results of these two methods are staggeringly different. The mass inferred from gravity, the lensing mass, is typically about 5 times greater than the mass of all the visible stuff. The majority of the mass holding these colossal structures together is completely invisible, exactly matching the dark matter needed to explain galaxy rotations. Perhaps the most dramatic demonstration of dark matter's existence comes from a cosmic collision, an event known as the Bullet Cluster. This is actually 2 galaxy clusters that have smashed right through each other. When they collided, the clouds of hot, X-ray emitting gas within each cluster, which makes up most of the normal matter, interacted strongly, slamming into each other and slowing down, much like 2 clouds of smoke would in a collision. But the dark matter, which does not interact with anything except through gravity, passed right through the collision unaffected. By mapping the mass using gravitational lensing, astronomers could see that the bulk of the mass, the dark matter, was now separated from the normal matter. It was as if 2 ghosts had walked through a crowd, and we could see their outlines clearly even though they were invisible. This observation provided near irrefutable proof that dark matter is real, a substance distinct from the ordinary atoms we know. So what is this mysterious stuff? We know what it is not. It is not made of protons, neutrons, or electrons, the building blocks of everything we see around us. It does not interact with light or with itself in any significant way other than through its gravitational pull. The leading hypothesis is that dark matter consists of a new, as yet undiscovered type of elementary particle, one that was created in the hot Big Bang. Candidates range from WIMP, or weakly interacting massive particles, which are heavy and slow-moving, to actions, which are incredibly light. Decades of experiments deep underground, in space, and at particle colliders like the Large Hadron Collider have been searching for a direct sign of these particles, but so far they have remained elusive. This invisible scaffolding is not just a minor component of the universe, it is the primary architect of its large-scale structure. In the early universe, dark matter's gravity acted as a gravitational well, a focal point that attracted normal matter. Without dark matter's pull, the slight density fluctuations from the Big Bang would not have been strong enough to gather gas efficiently enough to form the first galaxies and stars. The magnificent cosmic web of filaments and voids that defines the universe is essentially a map of where dark matter condensed under its own gravity, with visible galaxies forming like glitter sprinkled along the invisible threads. If dark matter provided the invisible scaffolding, then we need to ask what provided the initial blueprint, the subtle variations that allowed gravity to begin its work of assembly. The answer lies in the oldest light we can see, a faint glow that fills the entire sky and serves as our ultimate baby picture of the universe. This is the cosmic microwave background radiation, or CMB. To understand its significance, we have to travel back to a time before the first stars, before the first atoms, to a moment just 380,000 years after the Big Bang. At this point, the universe was a seething, opaque fog. It was far too hot for atoms to exist. Instead, it was a plasma of free electrons and atomic nuclei. In this dense, hot soup, light was trapped. Photons couldn't travel more than a tiny distance before bouncing off a free electron, like light trying to penetrate the thickest possible fog. But as the universe continued to expand, it cooled. Eventually, it reached a temperature cool enough, around 3,000 degrees Celsius, for a monumental change to occur. Electrons were finally captured by protons, forming the first stable, neutral atoms, primarily hydrogen and helium. In this moment, known as recombination, the fog instantly lifted. With the free electrons now bound into atoms, the photons suddenly had a clear path. The light that had been trapped for all those millennia was set free in a flash, streaming outward in every direction. That first burst of light, once brilliant and hot, has been traveling through the expanding universe ever since. And as space has stretched over the ensuing 13.8 billion years, it has stretched the wavelengths of those primordial photons as well. They have been redshifted from visible light all the way down to the microwave part of the spectrum, cooled to a mere 2.7 degrees above absolute zero. This is the faint whisper we detect today as the cosmic microwave background, a uniform bath of radiation that permeates all of space. When this relic radiation was accidentally discovered in 1965 by Arno Penzias and Robert Wilson using a large radio antenna, it was a moment of triumph for the Big Bang theory. But the real secrets of the CMB were not in its mere existence, but in its exquisite detail. The first full sky map of this background, produced by the COBE satellite in the early 1990s, revealed two profound facts. First, the radiation was incredibly uniform, with a temperature that was the same in every direction to within a tiny fraction of a degree. This confirmed that the early universe was a remarkably smooth and homogeneous place. But second, and far more importantly, COBE detected minute variations, tiny fluctuations in temperature anisotropies amounting to only about 1 part in 100,000. These tiny ripples, these hotter and cooler spots, may seem insignificant, but they are arguably the most important structures ever measured. They represent the seeds of all structure in the universe. Those tiny temperature differences correspond directly to tiny differences in the density of the young cosmos. A slightly warmer spot in the CMB is a region where the plasma was a tiny bit denser. A slightly cooler spot is a region that was a little more sparse, and in those slight overdensities, gravity found its foothold. Over hundreds of millions of years, the relentless pull of gravity amplified these tiny imperfections. The denser patches, reinforced by the gravitational attraction of dark matter, began to attract more and more gas from their surroundings. They grew, collapsing under their own weight to form the first proto-galaxies and the seeds of the stars within them. The slightly emptier regions, meanwhile, evolved into the vast cosmic voids we see today. The entire cosmic web of galaxies, clusters, and superclusters that we mapped out earlier is nothing less than the grown-up version of this infant pattern imprinted on the CMB. Modern missions like the Planck spacecraft have mapped these fluctuations with stunning precision, turning the CMB from a blurry snapshot into a high-definition portrait of the infant universe. By analyzing the statistical patterns of these hot and cold spots, cosmologists can read the CMB like a cosmic barcode, extracting a wealth of information about the universe's composition, age, and fate. The size and distribution of the fluctuations tell us that ordinary atoms make up only about 5% of the universe's content, with dark matter comprising about 27%, a perfect match for the evidence from galaxy rotations and clusters. The patterns also confirm the existence of dark energy and its dominance. Furthermore, the characteristics of these ripples are a direct probe of the universe's very first moments, providing strong support for the theory of cosmic inflation, a period of fantastically rapid expansion in the first fraction of a second after the Big Bang that would have stretched quantum fluctuations to cosmic size, creating the initial density variations that we see frozen into the CMB. So when we look at a map of the cosmic microwave background, we are not just looking at a remnant of heat, we are looking at the primordial blueprint for everything. Every galaxy, every star, every planet, and every one of us exists because of the subtle gravitational seeds planted in that ancient light. It is the foundation upon which the entire history of the cosmos was built, a direct message from the universe's infancy that tells us how it all began and gives us the clues we need to understand its ultimate destiny. But if the cosmic microwave background gives us the blueprint, it also presents us with a puzzle. Why is the universe so incredibly uniform? Why does the temperature of that ancient light look almost exactly the same in every direction we look? This might seem like a good thing, a sign of a well-behaved cosmos, but for physicists, it was a major problem known as the horizon problem. To understand why, think about two opposite sides of the observable universe. The light from those regions is just now reaching us, meaning for the first time in 13.8 billion years, we can see them. But here's the catch, those two regions on opposite horizons have never been in contact with each other before. There hasn't been enough time since the Big Bang for light or any form of information to travel between them. They are causally disconnected, like two strangers on opposite sides of a vast ocean who have never met. Yet when we observe them, they have the same temperature, the same density, the same properties to an astonishing degree of precision. How could they have coordinated themselves so perfectly if they were never in touch? It would be like walking into a massive concert hall and finding that every single person, without any prior communication, is wearing the exact same outfit down to the smallest detail. This horizon problem, along with a few other cosmological conundrums, pointed to a flaw in the standard Big Bang model. It suggested that the universe we see must have originated from a region that was initially in causal contact, a region that had time to smooth itself out into uniformity before being stretched apart. But the math of the classic Big Bang expansion didn't allow for that. The solution, proposed in the early 1980s by physicists like Alan Guth and others, was as radical as it was elegant, a theory known as cosmic inflation. The idea is that the universe underwent a breathtakingly brief but monumentally important period of hyper-expansion right at the very beginning. For a sliver of time so tiny it's almost impossible to comprehend, from about 10 to the power of negative 36 seconds to 10 to the power of negative 32 seconds after the Big Bang, the universe didn't just expand, it expanded exponentially. It doubled in size and then doubled again and again, over and over, perhaps 100 times or more, all within a fraction of a blink of an eye. This inflationary growth spurt is almost impossible to visualize with any everyday analogy, but we can try. Imagine an incredibly tiny speck, 1 billion times smaller than a single proton. Now, in less time than it takes for light to cross that speck, imagine that speck inflating to become larger than our entire observable universe today. That is the sheer, staggering scale of inflation. This process would have taken a tiny, subatomic patch of the early cosmos that was capable of becoming uniform through ordinary physics and stretched it to a size far, far greater than our entire observable horizon. The entire cosmos we can see, from one cosmic horizon to the other, was once a single, tiny, connected region that had plenty of time to even out its temperature and density before inflation blew it up to cosmic proportions. This elegantly solves the horizon problem. The reason the universe looks the same in all directions is because it was the same in all directions, originating from a small, homogeneous patch that was then inflated to become everything we can observe. But inflation did more than just iron out the wrinkles of the early universe. It also created the most important wrinkles of all. According to the theory, the driving force behind this exponential expansion was a hypothetical energy field called the inflaton field. As this field decayed, releasing its energy to create the hot, dense plasma of the conventional Big Bang, it wouldn't have decayed perfectly smoothly everywhere. Due to the inherent uncertainty of quantum mechanics, the inflaton field would have had tiny, random fluctuations, quantum jitters happening on the smallest possible scale. And here is the true magic of inflation. As space expanded at a fantastic rate, it stretched these infinitesimally small quantum fluctuations along with it, amplifying them to astronomical sizes. A quantum ripple that was once smaller than a subatomic particle was suddenly stretched to be light years across. These amplified fluctuations in the inflaton field translated directly into minuscule differences in the density of the energy being released. Regions where the field was slightly more dense ended up with a little more energy, and regions where it was less dense ended up with a little less. When inflation ended, these imprinted density variations were frozen into the fabric of the newborn hot universe. They became the seeds, the gravitational anchors for all future structure. The slightly denser patches had a bit more gravity, so they began to pull in surrounding matter. Over billions of years, these tiny initial overdensities grew through gravitational attraction, eventually collapsing to form the first proto-galaxies, then galaxies, clusters, and the entire cosmic web. The slightly less dense regions evolved into the great cosmic voids. In this way, the random, microscopic jitter of quantum fields in the first moment of time became the ultimate source of all macroscopic structure, from the grandest galaxy superclusters to the existence of our own planet. The pattern of hot and cold spots we see in the cosmic microwave background is a direct snapshot of these quantum fluctuations writ large across the sky. The theory of inflation also provides a compelling explanation for the overall geometry of the universe. One of the remarkable findings from missions like Planck is that the universe appears to be geometrically flat on the largest scales. This doesn't mean it's like a sheet of paper, but rather that parallel light beams stay parallel instead of converging or diverging over cosmic distances. Inflation naturally predicts this. Think of inflating a balloon. No matter how wrinkled or curved the surface of a small, uninflated balloon might be, as you blow it up to an immense size, any small section of its surface becomes flatter and flatter. In the same way, the incredible stretching of space during inflation would have smoothed out any initial large-scale curvature, leaving us with the flat universe we observe today. While inflation is a tremendously successful theory, explaining a host of observational facts with a single, elegant framework, it is important to remember that it is still a theory. The specific details of the inflaton field and the exact mechanics of the process are still active areas of research, with many different models competing. The quest now is to find a smoking gun, a unique prediction that different models make which could be tested. One of the most promising avenues is the search for primordial gravitational waves. The violent, rapid expansion of inflation would have sent powerful ripples through the very fabric of spacetime itself. these waves would have left a faint, distinctive curl-like pattern or polarization in the cosmic microwave background. Detecting this signal would be like hearing the echo of the Big Bang itself, providing direct evidence for inflation and potentially telling us about the energy scales at which it occurred. So far, this signal has eluded definitive detection, but the search continues with ever more sensitive experiments. Whether confirmed by future data or eventually superseded by an even more profound idea, cosmic inflation represents a monumental leap in our understanding, a theory that tells us the largest structures we see today were born from the smallest possible vibrations in the first fleeting moment of existence. Armed with this blueprint from the cosmic microwave background, the universe embarked on its greatest construction project, a process that would take billions of years and be directed by a single, relentless force, gravity. The story of how those minuscule temperature differences evolved into the majestic cosmic web is a tale of amplification, of tiny seeds growing into colossal structures through the patient, persistent pull of matter on itself. Imagine a perfectly smooth sheet of rubber stretched taut. Now place a single, minuscule marble in the center. The marble creates a tiny dimple. If you then scatter a fine dust over the sheet, the grains will naturally slide toward that dimple, gathering there and making it slightly deeper. As the dimple deepens, it attracts even more dust from a wider area. This is the essence of gravitational instability. The slightly denser regions revealed by the CMB were like those initial dimples in the fabric of space-time. They possessed just a tiny bit more gravitational pull than their surroundings. For the first few 100 million years, the universe was a dark and relatively simple place. The primordial gas, mostly hydrogen and helium, was smoothly distributed, but it was also falling into the invisible gravitational wells created by the dark matter. This dark matter, which does not interact with light and was therefore unaffected by the pressure of radiation, had already begun to clump together, forming a vast, invisible scaffolding. The ordinary matter, the gas that would eventually form stars and galaxies, simply followed this dark matter skeleton, flowing along its gravitational contours. Within these collapsing clouds of gas, pockets reached sufficient density and pressure to ignite the first nuclear furnaces, and the first stars blasted into existence, ending the cosmic dark ages and flooding the universe with light. These first stars were not isolated. They formed within the first proto-galaxies, which themselves were being drawn together along the emerging dark matter filaments. This growth was not a gentle process. It was a hierarchical ballet of merging and accretion. Smaller structures driven by gravity collided and merged to form larger ones. Small proto-galaxies combined to form larger galaxies, and those galaxies were themselves drawn into groups, which then fell into immense clusters at the intersections of the cosmic web. To visualize this epic evolution, scientists don't just look through telescopes. They build universes inside supercomputers. Cosmological simulations are our primary tool for watching billions of years of cosmic history unfold in a matter of hours. These are not simple animations. They are complex mathematical models that incorporate our best understanding of the laws of physics, especially gravity, and the known properties of dark matter and dark energy. The most sophisticated of these simulations, with names like Illustris TNG and Eagle, start with initial conditions that mirror the tiny fluctuations we see in the Planck CMB map. They populate a virtual space with billions of particles representing dark matter and gas. Then they set the equations of physics in motion and let the simulation run. What emerges is nothing short of breathtaking. Over virtual billions of years, the initially smooth distribution of particles begins to clump. A web-like pattern emerges spontaneously, with long, winding filaments of dark matter connecting at dense nodes where vast clusters of galaxies will form. Between these filaments, enormous voids open up, regions of startling emptiness that can be hundreds of millions of light years across. Watching these simulations is like seeing a time lapse of the entire cosmos growing up. We can witness galaxies forming, spinning, colliding, and quenching their star formation, all within the grand architecture of the web. The match between these simulated universes and the real universe observed by our telescopes is remarkably good. When we compare the cosmic web revealed by painstaking surveys that map the positions of millions of galaxies, like the Sloan Digital Sky Survey, to the web that emerges from the simulations, the resemblance is uncanny. Both show the same sponge-like filamentary structure, the same statistical distribution of cluster sizes, and the same vast, empty voids. This agreement is a powerful confirmation that our understanding of the basic process gravity acting on dark matter and gas, starting from the initial conditions of the CMB, is fundamentally correct. The simulations also reveal the dynamic nature of the web. Galaxies within the filaments are like cars on a cosmic highway, streaming along these dark matter roads toward the dense clusters at the intersections, which act as gravitational destinations. This continuous flow of matter is what keeps galaxy clusters growing and evolving even today. Yet, the story is not solely one of gravity's pull. The formation of the cosmic web is also a story of dramatic physics within the gas itself. As ordinary matter falls into the gravitational potential wells of the dark matter filaments, it doesn't just fall quietly. It can be heated to incredible temperatures, millions of degrees, causing it to glow in X-rays. This hot gas, which contains more mass than all the stars in all the galaxies within a cluster, is a major component of the web that is invisible to optical telescopes but clearly visible to X-ray observatories like Chandra. Furthermore, the simulations show that feedback processes, especially from supermassive black holes at the centers of galaxies, play a crucial role. When these black holes feed, they can unleash tremendous jets of energy that heat the surrounding gas, preventing it from cooling and forming new stars. This feedback regulates the growth of galaxies and helps shape the intricate balance of hot and cold gas we see within the cosmic web, proving that while gravity draws the outline, the finer details are painted by a much more complex set of physical processes. So we have this cosmic web, a vast scaffolding of dark matter filaments, and within its gravitational riverways, the raw material for galaxies begins to flow. But how does that primordial gas, mostly hydrogen and helium, actually transform into the diverse galactic cities we see today? The journey begins within the protective embrace of dark matter halos. Think of these halos as immense, invisible gravitational pots. In the early universe, these pots were relatively small, but as gravity worked its magic, they grew by pulling in more dark matter and, crucially, the surrounding clouds of pristine gas. As a gas cloud falls into one of these halos, it doesn't just settle quietly. It carries energy, angular momentum, and it begins to collapse under its own weight. The physics here is a delicate dance. The gas can radiate away heat, allowing it to cool and condense further. As it becomes denser, pockets within it reach a critical threshold where the pressure and temperature are so immense that nuclear fusion ignites. And just like that, the first stars are born, lighting up the darkness and marking the true birth of a galaxy. These first stars, often called population 3 stars, were not like our Sun. They were behemoths, hundreds of times more massive, burning ferociously bright and dying young in spectacular supernova explosions. These explosions were crucially important. They seeded the surrounding gas with the first heavy elements, atoms like carbon, oxygen, and iron forged in the stellar furnaces and blasted out into space. This enriched gas, now containing the building blocks of planets and life, would form the next generations of stars. Over time, through a process known as hierarchical merging, smaller protogalaxies, each with their own dark matter halo and population of stars, were drawn together by gravity and collided, merging to build larger and larger galaxies. Our own Milky Way, for instance, is a product of this long history of galactic cannibalism. having consumed numerous smaller dwarf galaxies over billions of years to achieve its current majestic scale. This process of growth and interaction is the primary sculptor of a galaxy's shape, leading to the three main types we classify today: spirals, ellipticals, and irregulars. A beautiful spiral galaxy like Andromeda or our Milky Way is essentially a galactic metropolis that has enjoyed a relatively quiet life. It has a large, rotating disk of gas and stars, often with elegant arms winding out from a central bulge. These arms are not permanent structures. They are density waves like traffic jams moving through the disk, compressing gas and triggering new waves of star formation. The vibrant blue light of young, hot stars traces these spiral arms. For a spiral to maintain its delicate disk, it needs a steady supply of cold gas to fuel star formation, and importantly, it must avoid major collisions that would disrupt its orderly rotation. An elliptical galaxy, on the other hand, is the end result of a galactic traffic pile-up. When two spiral galaxies of roughly similar size collide, the event is catastrophic. Unlike the stars within them, which are so far apart they simply pass by each other, the vast clouds of gas and dust slam together violently. This triggers a ferocious burst of star formation, quickly using up the available fuel. The gravitational forces of the merger completely randomize the orderly orbits of the stars, transforming the two spinning disks into a single, football-shaped blob of stars. An elliptical galaxy is a retirement community for stars. Its stars orbit the center in every direction like a swarm of bees. Without a rotating disk of cold gas, there is no fuel for new star birth. The population of stars ages together, giving ellipticals their characteristic reddish-yellow glow from older, cooler stars. They are found most often at the crowded intersections of the cosmic web, in the hearts of galaxy clusters where mergers are frequent. Then there are the irregular galaxies, the quirky individualists of the cosmos. These are often smaller galaxies that lack a defined shape, appearing as chaotic splotches of light. Their irregularity can be a sign of youth, a galaxy still in the process of formation, or it can be the result of a near miss, a gravitational interaction with a larger neighbor that twisted and distorted its structure without triggering a full merger. The Large and Small Magellanic Clouds, visible from the southern hemisphere, are classic irregular dwarf galaxies being gravitationally influenced by our Milky Way. The appearance of a galaxy is not fixed for eternity. It evolves dramatically over cosmic time. If we could fast forward through billions of years, we would see a universe that was much more chaotic in its youth. The early universe was filled with smaller, clumpier, and more irregular galaxies, actively colliding and forming stars at a rate far exceeding what we see today. As the universe aged and expanded, the frequency of these major mergers decreased. Galaxies began to settle down. Spiral galaxies that managed to avoid a major collision refined their disks, and many developed a central bar, a straight structure of stars that can help funnel gas inward to fuel star formation. The overall rate of star formation across the universe has been in decline for billions of years. Today, we live in a relatively quieter cosmic era where the brilliant starbursts of galaxy mergers are less common, and many galaxies are slowly using up their remaining reserves of gas. The story of a galaxy is a story of its interactions, a constant tug of war between the gravity that pulls things together and the dynamical processes that shape its final form, a narrative written in the light of its stars and the architecture of its structure. All those galaxies with their billions of stars are more than just beautiful points of light. They are the universe's great factories, and within them, individual stars play the most dramatic roles as both creators and destroyers. The life cycle of a star is a story of a constant battle between two fundamental forces, the crushing force of gravity and the explosive power of nuclear fusion. It begins in the cold, dark depths of space, within vast clouds of gas and dust known as molecular clouds. These nebulae are the nurseries of the cosmos, and they are far from empty. A single cloud can contain enough material to form thousands of stars like our Sun. For eons, this gas drifts quietly, but then something disturbs the equilibrium. It might be the shock wave from a nearby supernova explosion or the gravitational ripple of a passing galaxy. This disturbance causes a denser patch within the cloud to begin collapsing under its own gravity. As this pocket of gas contracts, it spins faster, much like a figure skater pulling in their arms, and it flattens into a rotating disk. The vast majority of the material falls inward, forming a hot, dense core at the center called a protostar. This is a furious, chaotic adolescence. Outflows of gas erupt from the protostar's poles, shooting into space, while the remaining material in the disk slowly clumps together to form planets, asteroids, and comets. Deep within the core, the pressure and temperature climb to unimaginable heights. When the core temperature reaches about 15 million degrees Celsius, a monumental transition occurs. The intense heat and pressure overcome the mutual repulsion of atomic nuclei, forcing hydrogen atoms to slam together and fuse into helium. This process, nuclear fusion, releases a tremendous amount of energy according to Einstein's famous equation, E equals mc squared. A tiny amount of mass is converted into a colossal amount of pure energy. This energy, radiating outward from the core, creates an immense pressure that finally halts the gravitational collapse. A stable balance is achieved and a new star ignites, shining brightly against the darkness. The mass of a star at its birth is the single most important factor that dictates its entire life story, its personality, and its ultimate fate. A star like our Sun, what astronomers call a low-mass star, leads a long, stable, and relatively quiet life. For billions of years, it will fuse hydrogen into helium in its core, burning through its fuel at a steady, reliable pace. This main sequence phase is the adulthood of a star, and it constitutes the vast majority of its lifespan. But eventually, even a star's vast reservoir of hydrogen runs low. When the core hydrogen is depleted, the balance of power shifts. Without the outward pressure from fusion, gravity begins to win again. The star's core contracts, growing even hotter and denser. This new heat ignites a shell of hydrogen fusion around the inert helium core, causing the star's outer layers to expand dramatically. The star bloats into a red giant, its surface cooling and turning a distinctive red hue. If our Sun were to go through this phase, its outer atmosphere would swell to engulf the orbits of Mercury, Venus, and even Earth. Meanwhile, the helium core, now compressed and heated to over 100 million degrees, faces its own dramatic moment. In a sudden and violent event known as the helium flash, the core ignites and begins fusing helium into carbon and oxygen. For a time, the star finds a new, unstable equilibrium. But this phase is relatively short-lived. The helium fuel is used up quickly, and the star's fate is sealed by its relatively low mass. It cannot generate enough pressure and heat to fuse the carbon and oxygen into heavier elements. The star begins to pulsate, shedding its outer layers into space in a series of beautiful, glowing shells. This expelled cloud of gas, illuminated by the intense ultraviolet radiation from the hot, exposed core, creates one of the most breathtaking sights in the universe, a planetary nebula. These intricate, often symmetrical clouds, with names like the Ring Nebula or the Helix Nebula, are the final, parting gifts of Sun-like stars. At the center, all that remains is the star's incredibly dense core, a white dwarf. About the size of Earth but containing a mass similar to the Sun, a white dwarf is a fantastic object. It no longer undergoes fusion. It simply glows with residual heat, slowly cooling over billions of years into a cold, dark stellar ember known as a black dwarf. For stars born with much greater mass, however, the story is far more spectacular and violent. High-mass stars live fast and die young. They burn their hydrogen fuel with ferocious intensity, shining with a brilliant blue-white light and lasting only a few million years, a mere blink in cosmic time compared to the 10-billion-year life of a star like our Sun. Their immense gravity creates cores that become unimaginably hot and dense. After burning through hydrogen to form a helium core, they don't stop. They begin to fuse helium into carbon, then carbon into neon, oxygen, silicon, and so on, like a multi-layered onion. Each successive fusion stage happens faster and at a higher temperature. In its final days, a massive star becomes a cosmic forge, creating elements all the way up to iron in its core. But iron is a dead end. Fusing iron atoms does not release energy, it consumes it. Suddenly, the star's core has no energy source to support itself against the crushing weight of the outer layers. In less than a second, the balance is shattered. The core collapses from a size roughly that of Earth to a ball of neutrons only about 12 miles across. The outer layers of the star, with nothing to support them, come crashing down at nearly a quarter the speed of light, only to rebound off the incredibly dense new core in the most powerful explosion known in the universe, a supernova. For a brief period, a single supernova can outshine its entire host galaxy. The energy released in this cataclysm is so immense that it forges elements heavier than iron, gold, silver, uranium, and all the other complex atoms that make up our world and our bodies. The explosion blasts these newly forged elements, along with the others created during the star's life, far out into the interstellar medium. The remnant of this titanic explosion can take two forms. If the collapsing core is between about 1.4 and 3 times the mass of our Sun, it will become a neutron star, an object so dense that a single teaspoon of its material would weigh billions of tons. Some neutron stars, called pulsars, spin rapidly, emitting beams of radiation that sweep across space like a cosmic lighthouse. If the core is more than about 3 solar masses, not even the pressure of neutrons can halt the collapse. Gravity wins completely, and the core continues to collapse into a singularity, forming a black hole, a region of space-time where gravity is so strong that not even light can escape. Whether through the gentle puff of a planetary nebula or the violent blast of a supernova, the death of stars is as crucial to the cosmos as their birth. This stellar recycling is the source of almost every element in the universe heavier than hydrogen and helium. The carbon in our cells, the oxygen we breathe, the iron in our blood, and the calcium in our bones were all forged in the hearts of long-dead stars. The beautiful nebulae we admire in telescope images are both the cradles and the graves of stars, clouds of gas and dust seeded with the heavy elements necessary for rocky planets and ultimately for life itself. We are quite literally made of stardust. The legacy of generations of stars that lived and died before our Sun was even a glimmer in a molecular cloud. But this cosmic drama of stellar life and death, of forging elements across billions of years, all plays out on a stage whose very nature is far more bizarre and wondrous than the simple, empty void we might imagine. To truly understand the motions of the cosmos, from the orbit of a planet to the collision of galaxies, we had to move beyond the familiar force described by Isaac Newton. Newton saw gravity as an instantaneous, mysterious force acting at a distance, a pull between any two objects with mass. And for centuries, this theory worked spectacularly well, predicting the motions of planets with incredible precision. But it left a fundamental question unanswered. How does gravity work? What is the mechanism that allows the Sun to reach across 93 million miles of empty space to hold the Earth in its orbit? The answer arrived in 1915 with Albert Einstein's revolutionary general theory of relativity, which completely redefined our conception of gravity. Einstein proposed that space and time are not separate, passive backgrounds for cosmic events. Instead, they are woven together into a single, four-dimensional fabric called space-time. And this fabric is not rigid, it is dynamic and flexible. The key insight of general relativity is that mass and energy tell spacetime how to curve, and curved spacetime tells mass and energy how to move. A massive object like our Sun creates a depression in the spacetime fabric, much like a heavy bowling ball placed on a stretched rubber sheet. The Earth, then, is not being pulled by some invisible string from the Sun. It is simply following the straightest possible path through the curved spacetime around the Sun. That path in the warped geometry around a massive object is what we perceive as an orbit. Gravity isn't a force in the traditional sense, it is a consequence of geometry. This warping of spacetime has several dramatic and observable consequences that go far beyond Newtonian predictions. One of the first confirmed was the bending of starlight. Einstein calculated that if spacetime is curved near a massive object, then even light, which has no mass, must follow that curvature. Its path would be bent. During a total solar eclipse in 1919, astronomers led by Arthur Eddington measured the apparent positions of stars near the Sun's obscured disk. They found that the star's light, passing close to the Sun's immense gravitational field, was indeed deflected by exactly the amount Einstein's equations predicted, not Newton's. This was a monumental victory for general relativity, proving that light itself falls in a gravitational field. This effect, known as gravitational lensing, has become one of the most powerful tools in modern astronomy. Think of spacetime curvature as a giant cosmic lens. When light from a very distant object, like a galaxy or a quasar, travels toward us and passes through the warped spacetime around a massive foreground object, such as a galaxy cluster, its path is bent. From our perspective, this can distort and magnify the image of the background source in spectacular ways. In weak lensing, the distant galaxy might simply appear stretched into a faint arc, a telltale sign of the invisible mass in the foreground. But in strong lensing, the effects are even more dramatic. The background object can be smeared into multiple, separate images, or even stretched into a complete or partial circle of light encircling the foreground lens. These perfect rings are known as Einstein rings, and they are a breathtaking visual confirmation of the warped universe Einstein described. Gravitational lensing does more than just create beautiful cosmic mirages, it allows us to see the unseeable. Because the amount of bending depends on the total mass of the foreground object, lensing provides a direct way to weigh galaxy clusters, revealing the vast amounts of dark matter that would otherwise be completely invisible. It also acts as a natural telescope, magnifying galaxies that are so far away and faint they would be impossible to observe with our own instruments. The Hubble Space Telescope's deepest field images are filled with these faint, distorted arcs, each one a distant galaxy whose light has been amplified by the gravity of intervening matter, giving us a glimpse of the universe's earliest epochs. The phenomenon even allows us to map the distribution of dark matter directly by carefully measuring the subtle distortions of millions of background galaxies, a technique called weak gravitational lensing that charts the invisible skeleton of the cosmic web. Another profound prediction of general relativity is gravitational time dilation. Because space and time are inextricably linked as space-time, the warping of space by gravity also affects the flow of time. Clocks tick more slowly in stronger gravitational fields. A clock on the surface of the Earth, for instance, runs very slightly slower than a clock on a GPS satellite in orbit. If this effect weren't precisely accounted for, the GPS system we rely on for navigation would accumulate errors of several miles within a single day. This isn't just a theoretical curiosity, it's a daily validation of Einstein's theory that our modern technology depends upon. Near the event horizon of a black hole, where gravity is unimaginably strong, this time dilation effect becomes extreme. To a distant observer, time for an object falling into a black hole would appear to slow to a halt, forever freezing at the moment it crosses the horizon. The object itself, of course, experiences its own time normally and would continue its fateful plunge. But for these cosmic seeds to grow, they needed a universe that could cool and quiet down enough for gravity to take over, and this brings us to a pivotal moment known as the cosmic dawn. After the fury of inflation and the seething plasma of the early universe, the cosmos entered a period often called the Dark Ages. For millions of years, the universe was a vast, featureless expanse of neutral hydrogen and helium gas, still echoing with the faint afterglow of the CMB but otherwise utterly dark. There were no stars, no galaxies, no sources of light. It was within this profound darkness that the quantum seeds planted by inflation began to stir. The slightly denser patches of dark matter continued their slow, relentless gravitational collapse, pulling the ordinary gas along with them. Deep within these collapsing clouds, pockets of gas became increasingly dense and hot. And then, somewhere in one of those primordial clouds, a threshold was crossed. The pressure and temperature at the core of a gas cloud became so immense that hydrogen atoms, which normally repel each other, were forced together with enough violence to fuse into helium. In a flash of light, the first star was born, piercing the cosmic darkness and heralding the end of the Dark Ages. This first generation of stars was unlike anything that exists today. They were true behemoths, perhaps hundreds of times more massive than our Sun, composed only of the pristine hydrogen and helium forged in the Big Bang. Without any heavier elements to help them radiate away heat, these stars had to burn at ferociously high temperatures to support themselves against their own immense gravity. They lived spectacularly bright but very short lives, exploding as supernova after only a few million years. These cataclysmic deaths were as important as their births. They blasted space with the first heavy elements carbon, oxygen, iron forged in their cores, polluting the pristine gas from which the next generation of stars would form. They also flooded the universe with intense ultraviolet radiation that began to tear apart the neutral hydrogen atoms throughout space, a process called reionization, which eventually made the universe transparent to ultraviolet light and set the stage for the galaxies we see today. The cosmic dawn was not a gentle sunrise. It was a series of brilliant, violent flashes that fundamentally transformed the cosmos, all triggered by the gravitational amplification of those initial quantum ripples. This incredible narrative, which connects the fuzzy, probabilistic world of the quantum to the grand, deterministic architecture of the cosmos, presents us with one of the most profound and stubborn puzzles in all of physics. The very mechanism that created the seeds of structure, the amplification of quantum fluctuations during inflation, relies on a handshake between two theories that, in our current understanding, fundamentally refuse to agree. On one hand, we have quantum mechanics, which describes the bizarre, probabilistic behavior of the very small with unparalleled accuracy. On the other, we have Einstein's theory of general relativity, which masterfully describes the nature of gravity and the large-scale structure of spacetime. Both theories are spectacularly successful in their own domains, yet they are built on entirely different mathematical and conceptual foundations. And when we try to apply them both to the same extreme environment, the first fraction of a second after the Big Bang, when the entire universe was smaller than an atom and governed by quantum laws, the framework breaks down completely. The core of the conflict lies in how each theory views reality. Quantum mechanics is inherently probabilistic. It tells us that particles don't have definite properties until they are measured. They exist in a haze of probabilities, a superposition of all possible states. Events at the quantum level are not certain but are governed by chance. General relativity, in stark contrast, is deterministic and geometric. It describes a smooth, continuous, and predictable fabric of spacetime that responds in a precise way to the matter and energy within it. It is a classical theory in the sense that it has no room for probability or uncertainty. If you know the state of the universe at one moment, you can, in principle, calculate its entire future and past. Trying to merge these two visions is like trying to write a single set of rules for a game that is simultaneously played with dice and on a perfectly predictable chessboard. The singularity at the beginning of the Big Bang and the core of a black hole are arenas where both the incredibly small and the immensely powerful force of gravity come into play, and our current physics simply cannot describe what happens there. We need a theory of quantum gravity. The quest for this final theory is the great frontier of fundamental physics. Several promising paths are being explored, though a definitive answer remains elusive. String theory proposes that the fundamental constituents of reality are not point-like particles, but incredibly tiny, vibrating loops of energy. Different vibrations of these strings would correspond to different particles, including a hypothetical particle called the graviton that would mediate the force of gravity, potentially bringing it into the quantum fold. Another leading approach is loop quantum gravity, which suggests that spacetime itself is not continuous but is made of discrete, quantized units, tiny, woven loops that give the fabric of the universe a pixelated structure at the smallest possible scale, the Planck length. There are other ideas like causal dynamical triangulations, which model spacetime as being built from simple, geometric building blocks. Each of these approaches has its own strengths and profound implications, but so far, none has produced a testable prediction that would allow us to confirm or refute it with current technology. This unresolved tension is not just an academic exercise, it points to a deeper mystery about the nature of our universe. The fact that quantum fluctuations, purely random events on a microscopic scale, could be stretched to become the deterministic blueprint for galaxies, stars, and planets suggests a deep and mysterious link between the smallest and largest scales of existence. It forces us to ask whether the universe was truly born from a random quantum event, or if there is a deeper order that we have not yet uncovered. The interface between quantum mechanics and gravity remains the final barrier to a complete understanding of the universe's earliest moments, a puzzle that challenges our most basic concepts of space, time, and reality itself. Unlocking it would not only tell us what happened at the absolute beginning, but would also reveal the true, fundamental nature of the cosmic stage upon which the entire history of the universe has played out. This journey through the cosmos, from quantum ripples to galactic superclusters, inevitably leads us to a deeply personal and profound question. If the fundamental constants of nature were even slightly different, the universe as we know it would not exist. The strength of gravity, the force of the electromagnetic interaction, the mass of a proton, these and dozens of other numbers seem to be set with astonishing precision. If gravity were a fraction stronger, the universe would have collapsed back on itself shortly after the Big Bang. If it were a fraction weaker, matter would never have clumped together to form stars and galaxies. If the nuclear forces were altered, stars might not burn, or the complex elements essential for life would never be forged. This apparent fine-tuning leads directly to a concept known as the anthropic principle, an idea that attempts to frame our existence within the context of the cosmos we observe. In its simplest form, the weak anthropic principle is almost a statement of the obvious. It suggests that we, as conscious observers, can only find ourselves in a universe capable of sustaining life. The universe must have properties that allow observers to arise, otherwise we wouldn't be here to notice it. It's a selection effect. Imagine a puddle waking up one morning and looking at the hole it sits in. The puddle might marvel at how perfectly the hole fits its shape, with every bump and contour exactly matching its own. This hole was made for me, the puddle might think. But of course, that's looking at it backward. The hole wasn't designed for the puddle simply conforms to the shape of the hole. In the same way, the weak anthropic principle argues that we shouldn't be surprised that the universe is compatible with our existence. We are the products of its laws, not the other way around. We are a cosmic afterthought, a consequence of the universe's properties that emerged billions of years after the constants were set. However, the sheer precision of this apparent fine-tuning has led some scientists and philosophers to propose a stronger version of the anthropic principle. The strong anthropic principle takes a much more radical stance. It posits that the universe must have those properties that allow life to develop at some stage in its history. The word "must" is crucial here. This version implies that the laws of nature and the values of the constants are in some sense inevitable, perhaps because the existence of observers is a necessary component for the universe to be fully realized. This perspective often veers into philosophical and even theological territory, suggesting a form of teleology or purpose built into the fabric of reality, where the cosmos is in some way compelled to give rise to consciousness. Between these two interpretations lies a third, and for many physicists, a more compelling explanation that draws on the frontiers of cosmology, the multiverse. The multiverse hypothesis proposes that our universe, with its specific set of laws and constants, is not the only one. Instead, it is just one bubble in a vast, perhaps infinite, cosmic foam of universes, each with its own unique physical laws. In this grand landscape, the fundamental constants might not be fine-tuned at all, but rather randomly selected. Most of these universes would be stillborn, collapsing instantly, or expanding so rapidly that no atoms can form, or governed by forces too weak to create any structure. They would be dark, empty, and lifeless, but in a mind-bogglingly vast multiverse, every possible combination of constants will be realized somewhere. By pure chance, a tiny fraction of universes will, like ours, have just the right recipe for stars, planets, and life. We find ourselves in one of these rare, hospitable universes not because it was designed for us, but simply because we couldn't exist anywhere else. This idea finds a natural home in the theory of eternal inflation, where the inflationary period that shaped our early universe is a perpetual process, continually spawning new pocket universes with different properties. String theory, too, suggests the possibility of a vast landscape of potential universes, each corresponding to a different way for the extra dimensions proposed by the theory to be compactified. The multiverse doesn't explain why our constants have the values they do. It simply reframes the question, instead of asking, why are the constants so life-friendly? We ask, why do we find ourselves in a life-friendly universe? The answer becomes a statistical certainty given a sufficiently large sample size. Yet, the multiverse idea is not without its critics. A major challenge is its testability. If these other universes are causally disconnected from our own, existing in a domain beyond our cosmic horizon, can we ever gather empirical evidence for their existence? Some scientists argue that until a theory makes a falsifiable prediction, it remains in the realm of metaphysics rather than physics. Proponents, however, point to potential indirect evidence. For instance, if our universe collided with another bubble universe in the distant past, it might have left an imprint on the cosmic microwave background, a peculiar pattern of hot and cold spots that we could, in principle, detect. So far, no such definitive evidence has been found. Ultimately, the anthropic principle, in all its forms, forces us to confront the extraordinary unlikelihood of our own existence. Whether it's seen as a tautology, a necessity, or a selection effect in a multiverse, it highlights that our ability to ponder the cosmos is itself a cosmic phenomenon. The laws of physics are not just abstract equations. They are the rules that allowed for the gradual assembly of complexity over billions of years, leading from the first stars to planets, biology, and eventually to a species that can look back at the universe and ask why it looks the way it does. Our very presence is a testament to a long chain of cosmic events, each dependent on the precise values of those fundamental constants. This doesn't necessarily provide a final answer, but it deepens the mystery and the wonder, connecting our most intimate question, why are we here, to the most fundamental workings of reality itself. This exploration of the anthropic principle inevitably propels us toward one of the most mind-expanding concepts in all of cosmology, an idea that pushes the very boundaries of science itself, the multiverse hypothesis. The notion that our entire observable cosmos, with its hundreds of billions of galaxies stretching across nearly 100 billion light-years, might be just a single bubble in a vast, perhaps infinite, cosmic foam of universes is staggering. And while it may sound like pure science fiction, this idea emerges as a natural, though speculative, consequence of our most successful theories about the very beginning of everything. The primary engine for this incredible possibility is the theory of cosmic inflation we discussed earlier. The idea of a brief, hyper-fast expansion that smoothed and flattened our universe is powerful, but what if that inflationary period wasn't a one-time event? What if it's eternal? This is the theory of eternal inflation. Imagine the inflationary field, the driving force behind the rapid expansion, not as a single firecracker that ignites and fizzles out, but as a vast ocean of energy. In most regions of this ocean, the inflationary field decays, converting its energy into the hot plasma of a standard Big Bang, creating what we would call a universe like our own. But due to quantum fluctuations, some regions of this primordial energy field never decay. In these pockets, the inflationary process continues unabated, expanding at an exponential rate far faster than the bubbles where it has stopped. As these inflating regions grow, they themselves spawn new bubbles where inflation ends and new universes are born. This process becomes self-perpetuating, creating an endless, ever-growing tree of universes, a multiverse. Each of these bubble universes would be causally disconnected from all the others, forever separated by exponentially expanding space, making them islands in a truly unimaginable metacosmos. Now, if each bubble universe forms from a random quantum fluctuation in the inflattened field, it's plausible that the properties of that bubble could be different. The way the field decays could determine the fundamental constants of physics within that new universe. In one bubble, the force of gravity might be exponentially stronger, causing it to collapse back into a singularity almost instantly. In another, the electromagnetic force might be too weak for atoms to ever form, resulting in a perpetual, lifeless fog of particles. The vast majority of these universes would be stillborn, chaotic, or utterly barren. But in a truly infinite multiverse, every possible combination of physical constants and laws must be realized somewhere. By sheer statistical inevitability, a tiny fraction of these bubbles would, purely by chance, have the exact right recipe for stability, longevity, and complexity. Our universe, with its seemingly fine-tuned constants, would simply be one of those rare, fortunate outliers where the conditions are just right for galaxies, stars, planets, and life to emerge. We don't live in a special universe. We live in a universe that is habitable, and we couldn't exist in any of the uninhabitable ones. Another compelling path to the multiverse comes from string theory, the ambitious attempt to unify all forces and particles by modeling them as tiny, vibrating strings. One of the predictions of string theory is the existence of extra, curled-up dimensions of space beyond the three we experience. The way these dimensions are compactified, their specific shape and size, determines the laws of physics that manifest in the resulting universe. String theory doesn't predict one unique way for this to happen. Instead, it suggests a colossal landscape of possibilities, often estimated to be around 10 to the 500 different vacuum states. Each of these states corresponds to a different universe with its own unique set of physical laws and constants. Our universe, then, would just be one point in this inconceivably vast landscape. The apparent fine-tuning is again explained away not by design, but by selection. We find ourselves in a universe compatible with our existence because it's the only type of universe where such a question could ever be asked. Beyond these two leading ideas, other multiverse concepts add to the tapestry. The many worlds interpretation of quantum mechanics, for instance, proposes that every time a quantum event has multiple possible outcomes, the entire universe branches, realizing all possibilities in separate, non-communicating timelines. While this is a different kind of multiverse from the cosmic bubbles of eternal inflation, it further illustrates how our best theories seem to point toward a reality far grander and more populous than a single universe. The multiverse hypothesis, for all its theoretical appeal, faces a significant and legitimate challenge: testability. If these other universes are permanently beyond our cosmic horizon, separated from us by realms of space expanding faster than light can cross, how can we ever gather empirical evidence for their existence? This leads some critics to argue that the multiverse is not science, but rather a philosophical or even metaphysical idea. Proponents, however, point to potential indirect signatures. For example, if our bubble universe collided with a neighboring bubble in the distant past, the shockwave from that cosmic fender bender could have left a distinct anisotropic pattern in the cosmic microwave background, a kind of bruise on the oldest light we can see. Astronomers have actively searched for such patterns, and while some intriguing but unconfirmed anomalies have been reported, there is no definitive evidence yet. Other potential tests involve looking for subtle imprints of the primordial inflationary field that might hint at its eternal nature. Whether the multiverse remains a powerful theoretical speculation or eventually graduates to a testable scientific theory, its value lies in how it fundamentally shifts our perspective. It challenges the assumption that our universe is all there is, forcing us to consider a reality of literally cosmic proportions. It reframes the question of why our universe looks the way it does from, why are the laws of physics so perfect for life, to what does the distribution of laws look like across the multiverse, and how typical or atypical is our own existence. This is a profoundly humbling thought. The majestic spiral galaxies, the brilliant nebulae, the very laws that allow for atoms and molecules, might not be the central feature of reality, but merely a local bylaw in one unremarkable town in an infinite cosmic country. It suggests that the great cosmic story we have been unraveling, from quantum fluctuations to the cosmic web, might be just one version of that story, one narrative in a library of universes containing every story that can possibly be told. But this incredible journey through the cosmos, from the multiverse to the fundamental laws, leads us to perhaps the most intimate and existential question of all, one that lies at the very heart of our existence. Given everything we know about the violent symmetries of the early universe, there is a profound puzzle that challenges our understanding of creation itself. In the first moments after the Big Bang, the universe was a seething cauldron of energy, and according to our best theories, this energy should have been converted into matter and antimatter in perfectly equal amounts. For every proton created, an antiproton should have been born. For every electron, a positron. Matter and antimatter are essentially mirror images of each other, equal but oppositely charged. And when a particle meets its antiparticle, they annihilate each other in a flash of pure energy, returning to the state from which they came. This presents us with a staggering cosmic contradiction. If the early universe produced equal parts matter and antimatter, they should have completely annihilated one another, leaving behind a universe containing nothing but a fading sea of photons, our eternal, featureless light. There would be no atoms, no stars, no planets, and certainly no one to ponder this outcome. The fact that you exist to watch this video, that our universe is filled with galaxies and gas and dust, is undeniable proof that this perfect symmetry was broken. Somehow, for every billion pairs of matter and antimatter particles that annihilated in the early cosmos, one single matter particle was left over. That 1 in a billion survivor is the reason anything exists at all. All the stars, planets, and people in the observable universe are made from that tiny, inexplicable excess of matter. This is the mystery of baryon asymmetry, and solving it is one of the great quests of modern physics. The process that could have led to this overwhelming dominance of matter is called baryogenesis. For baryogenesis to occur, three conditions, first outlined by physicist Andrei Sakharov, must have been met in the early universe. First, there must be a process that violates the conservation of baryon number. A baryon is a heavy particle like a proton or neutron, and baryon number is a quantity that, in our everyday experience, seems to be perfectly conserved. Protons are stable and don't just disappear. The total number of baryons in a reaction appears constant. But for an excess of matter to be created, there had to be a way to create more baryons than antibaryons, breaking this apparent law. Second, the laws of physics must violate both charge symmetry and parity symmetry. This is a bit more subtle. Charge symmetry, or C-symmetry, means the laws should work the same for particles and their antiparticles. Parity, or P-symmetry, means the laws should be the same if you look at a reaction in a mirror. We know that these symmetries are violated in certain interactions of the weak nuclear force, but the level of violation observed is far too small to account for the matter surplus we see. The third Sakharov condition is that these processes must have occurred out of thermal equilibrium. If the universe was in a perfectly balanced thermal state, any budding matter excess would have been wiped out by reverse reactions. There needed to be a departure from this equilibrium, a moment of cosmic imbalance that allowed the asymmetry to be locked in permanently. The hunt is on to find a physical process in the early universe that satisfies all three of these conditions with sufficient vigor. One of the leading candidates involves the Higgs boson and the nature of the Higgs field, which gives particles their mass. In the extremely high-energy environment just after the Big Bang, the Higgs field might have undergone a phase transition, much like water freezing into ice. As the universe cooled, the Higgs field could have settled into its current state not smoothly, but through the formation of bubbles of the new phase. These expanding bubbles could have created the necessary conditions out of equilibrium, and interactions at the bubble walls might have preferentially produced more matter than antimatter. Another compelling idea involves neutrinos, the ghostly particles that barely interact with normal matter. If neutrinos are their own antiparticles, a special type of particle known as a Majorana fermion, then a process called leptogenesis could be the answer. In this scenario, the decay of very heavy, hypothetical right-handed neutrinos in the early universe could have produced a small excess of leptons, the family of particles that includes electrons and neutrinos. Through subtle interactions with the electroweak force, this lepton asymmetry could then have been converted into the baryon asymmetry we observe today, effectively turning an imbalance in lightweight neutrinos into the dominance of protons and neutrons. Yet, despite these elegant theoretical proposals, a definitive answer remains elusive. Experiments like the Large Hadron Collider are searching for new particles and new sources of symmetry violation that could tip the scales. Observatories are studying the properties of neutrinos with ever greater precision to see if they hold the key. The mystery of why there is something rather than nothing is not just philosophical. It is a concrete, scientific question whose answer is written into the fabric of every atom in our bodies. The existence of our material world is a clue, a cosmic crime scene where the culprit, the physical law that favored matter, has left traces we are only just beginning to decipher. Finding the source of this primordial preference would complete a fundamental chapter in our story of the cosmos, explaining not just how the universe looks, but why it contains the essential ingredient for everything we hold familiar, us. All these individual galaxies and cosmic structures, from the quiet spirals to the colossal clusters, might seem randomly scattered across the void. But when we pull back the camera to view the cosmos on its very largest scales, a breathtaking and deeply fundamental pattern emerges. This pattern is described by a cornerstone idea in cosmology known as the cosmological principle. In essence, this principle makes two key assertions about the universe. First, it states that the universe is homogeneous. This doesn't mean that every single little patch of space has exactly the same number of galaxies, obviously. A galaxy cluster is much denser than a vast cosmic void. Instead, it means that if you take a large enough volume of space, a truly gigantic cube a few 100 million light-years on a side, the average density of matter within that volume will be roughly the same, no matter where you place your cube in the observable universe. The second assertion is that the universe is isotropic. This means it looks the same in every direction. There is no central point, no preferred axis, no cosmic up or down. From our vantage point, and from the perspective of any other observer in the cosmos, the large-scale universe presents a uniform appearance. This idea that we do not occupy a special or privileged location is a profound extension of the Copernican revolution, pushing it from our solar system to the entire cosmos. The evidence for this remarkable uniformity comes from two primary sources, each providing a snapshot of the universe at a very different age. The first line of evidence comes from immense three-dimensional maps of the nearby universe. Projects like the Sloan Digital Sky Survey have painstakingly measured the positions and distances of millions of galaxies, allowing us to construct a grand chart of our cosmic neighborhood. When you look at these maps, you don't just see a random scattering of points. You see the cosmic web in all its glory, an intricate lacework of galaxy filaments and vast, empty voids. This structure is undeniable, but the cosmological principle asks us to look at the statistical properties of this web. When astronomers analyze these maps, they find that if you smooth out the distribution, averaging over those immense volumes of space, the number of galaxies per cubic billion light-years is essentially the same everywhere we look. The spongy structure is consistent. The holes and threads have similar sizes and distributions whether we look toward the constellations of Virgo or Hydra. There is no sign of a grand, overarching gradient, no edge or center to the galaxy distribution within our observable horizon. We appear to be living in a universe that is, on the largest scales, evenly filled with matter. The second, and perhaps even more compelling, line of evidence comes from that ancient baby picture of the universe, the cosmic microwave background. The CMB is the ultimate test of isotropy. When we look at this afterglow, we are looking at the universe when it was only 380,000 years old, and we are seeing the surface of last scattering from all directions simultaneously. The most striking feature of the CMB, as first revealed by the COBE satellite, is its incredible smoothness. To a very high degree of precision, the temperature of this radiation is the same in every direction you point your telescope, at 2.725 degrees above absolute zero. This isotropy is powerful proof that the early universe was remarkably uniform. The hot and cold spots we see are minuscule variations on the order of 1 part in 100,000. To appreciate how smooth this is, if the CMB were an ocean, the height difference between the tallest wave and the deepest trough would be less than a centimeter. This incredible large-scale isotropy strongly supports the idea that the universe has no preferred direction, but the CMB also provides a subtle and brilliant test of homogeneity. You might think, if the universe looks the same in every direction from our point of view, couldn't it still be arranged in a shell-like structure with us at the center? A famous analogy is that if you were lost in a vast, homogeneous forest, the trees would appear isotropic around you, but that doesn't mean you are in a special place in the forest. It just means the forest is uniform. The CMB allows us to test this. The patterns of fluctuations in the CMB are not random. They have a characteristic size related to the distance sound waves could travel in the plasma during those first 380,000 years. By studying the statistical distribution of these hot and cold spots, cosmologists can determine the geometry of the universe. The results from missions like Planck show that the universe is geometrically flat on large scales, which is a direct prediction of a homogeneous and isotropic universe. A spherical or saddle-shaped universe would show a different pattern of spots. Furthermore, the fact that the statistical properties of the CMB fluctuations are the same everywhere on the sky tells us that the initial conditions were homogeneous. The seeds for all structure were evenly distributed. The universe wasn't just isotropic from our viewpoint, it was homogeneous from the very beginning. This large-scale uniformity has profound implications. It is the foundation upon which our entire modern understanding of cosmology is built. Without the assumption of homogeneity and isotropy, Einstein's equations of general relativity would be impossibly complex to solve for the entire universe. The cosmological principle allows us to apply these equations to the cosmos as a whole, leading directly to the Friedmann-Lemaitre-Robertson-Walker models that describe an expanding universe and predict the Big Bang. It tells us that the laws of physics are the same everywhere. The nuclear forces that power distant quasars, the gravitational constant that holds galaxy clusters together, and the speed of light are universal constants. This means we can use our local understanding of physics to confidently interpret events happening billions of light years away. The cosmological principle assures us that we are not in a cosmic zoo or a special exhibit. We are participants in a universe whose basic rules are consistent throughout space and time, allowing us to unravel its grand history from our tiny, unremarkable corner of the cosmos. Yet, with such a vast and intricate cosmic web sculpted by dark matter and propelled by dark energy, we are forced to confront the ultimate question, one that looks not to the past but to the far, far future. Where is all of this headed? The ultimate fate of our universe hinges on a cosmic tug-of-war, a battle between two opposing forces, the relentless outward push of dark energy and the eternal inward pull of gravity. Depending on which force ultimately wins, or if they reach a stalemate, the cosmos could end in one of several profoundly different ways, each more dramatic and mind-bending than the last. For much of the 20th century, the leading candidate for our cosmic destiny was the Big Crunch. This scenario imagines a universe that eventually stops expanding and begins to contract. The logic was straightforward. Gravity is an attractive force. If there were enough matter in the universe, its combined gravitational pull would gradually slow the expansion, halt it, and then reverse it. Galaxies would begin to fall back toward each other, space itself would start to shrink, and the universe would begin to heat up as it collapsed. The background temperature of space, currently just a few degrees above absolute zero, would rise. The cosmic microwave background would shift from microwaves to infrared, then to visible light, and eventually the night sky would glow as bright as a starry day. The final act would be a catastrophic collapse into an ultra-hot, ultra-dense state, a mirror image of the Big Bang, potentially ending in a singularity. It's a cyclical, almost poetic vision, a universe that ends as it began. However, the discovery of dark energy and the accelerating expansion has made the Big Crunch the least likely of our major scenarios. For gravity to win, the density of matter and energy in the universe would have to be high enough to overcome dark energy's repulsive push, and all our current measurements suggest that dark energy is not only dominant but is making that possibility increasingly remote. Instead, the prevailing view based on our current data points to a much colder, lonelier, and more gradual end, known as the heat death or the Big Freeze. In this scenario, dark energy remains constant, and the acceleration of the universe's expansion continues indefinitely. Billions of years from now, the universe will be a much darker place. As galaxy clusters are pushed ever further apart by the stretching of space, they will eventually be accelerated beyond one another's cosmic horizons. The light from distant galaxies will be redshifted so severely that their wavelengths will be stretched beyond the detectable limit, and they will effectively vanish from the observable universe of any future civilization. Our local group of galaxies, bound together by gravity, may merge into a single, giant elliptical galaxy, but beyond that, there will be nothing but an ever-deepening blackness. Within this isolated galaxy, the star-forming gas will slowly be used up. The last stars will flicker out, leaving behind a cosmic graveyard of stellar remnants, white dwarfs, neutron stars, and black holes. Even these remnants are not eternal. Over almost unimaginable timescales, trillions upon trillions of years, even white dwarfs and neutron stars will radiate away their remaining heat and cool to the temperature of the background universe, becoming cold, dark black dwarfs. And in a final, profound twist, thanks to quantum mechanics, even black holes are not truly permanent. They slowly evaporate by emitting a faint trickle of radiation, a process known as Hawking radiation. Once the last black hole has evaporated, the universe will contain only a sparse sea of subatomic particles and photons, all at the same infinitesimally low temperature. With no temperature differences, no hot spots or cold spots, no energy gradients can exist, and thus no work can be done. It is the ultimate state of thermodynamic equilibrium, a cosmic entropy maximum where the universe, for all intents and purposes, reaches a permanent and silent standstill. But the heat-death scenario assumes that the strength of dark energy, embodied by the cosmological constant, remains fixed over time. What if it doesn't? This leads us to the most violent and dramatic potential ending, the Big Rip. In this model, dark energy is not constant but grows stronger over time. Instead of a cosmological constant, it could be something called phantom energy, a form of dark energy with a truly bizarre property. Its energy density increases as the universe expands. If this is the case, the acceleration of the universe wouldn't just continue, it would become exponentially more ferocious. The repulsive force of dark energy would eventually overcome every force that holds structures together. The timeline is terrifyingly specific. First, galaxy clusters would be torn apart. Then, billions of years later, the Milky Way and all other galaxies would be shredded as the gravitational glue holding them together is overwhelmed. As the end draws near, planetary systems would be ripped from their stars. In the final minutes, stars and planets themselves would be vaporized as the repulsive force exceeds their own gravity. In the last fraction of a second, atoms, molecules, and even atomic nuclei would be torn asunder as the force binding quarks together is defeated. The universe would end not with a whimper, but with a literal tearing apart of the very fabric of space-time at the most fundamental level, leaving behind a barren, meaningless void of disconnected particles. While the evidence currently favors a constant dark energy, making the Big Rip less likely, it remains a haunting possibility that reminds us how much we still have to learn about the dominant component of our cosmos. Our understanding of cosmic destiny is not yet complete, and there are even more speculative ideas on the table. Some theories suggest that the vacuum of space might not be in its true lowest energy state, but is instead a false vacuum. If our universe were to somehow tunnel into a lower energy state, a bubble of true vacuum could form somewhere and expand at the speed of light, fundamentally altering the laws of physics as it goes and effectively erasing the universe as we know it. Others, inspired by the possibility of a multiverse, speculate about cyclical universes where a big crunch leads to a big bounce, or where colliding membranes in a higher dimensional space periodically create new Big Bangs. These are fascinating theoretical playgrounds, but for now, they remain firmly in the realm of speculation. The trajectory of our observable universe, as best we can measure it, points toward a cold and expanding future. The story of the cosmos, which began in a blaze of light and energy, appears to be headed for a final chapter of darkness and stillness, a quiet conclusion to the epic of existence that started nearly 14 billion years ago. But for all the cosmic truths we've uncovered, from the Big Bang to dark energy, there is a humbling reality we must always remember. Our entire understanding of the universe is not a direct, unfiltered view of reality as it is. Instead, it is a picture painstakingly assembled through a series of technological proxies, each with its own strengths, its own blind spots, and its own inherent limitations. The cosmos we perceive is, in a very real sense, a reflection of the tools we have built to observe it. This isn't a flaw, it's the very essence of the scientific journey. Every time we build a new instrument that can see the universe in a different way, we are essentially opening a new window in a previously shuttered room, revealing a part of the cosmic landscape that was always there but forever hidden from our view. Consider the most fundamental tool in astronomy, the telescope. For centuries, our view was confined to the narrow sliver of light our eyes can see. Galileo's primitive spyglass revealed moons orbiting Jupiter and the craters on our own moon, but it was utterly blind to the radio waves whispering from cold hydrogen clouds or the deadly gamma-ray screams of exploding stars. The universe was communicating with us in a full symphony of wavelengths, but we were only equipped to hear a single, quiet melody. This began to change in the 20th century. The discovery that light was part of a vast electromagnetic spectrum meant that the light from the cosmos came in many forms, from the long, lazy waves of radio to the incredibly energetic, short wavelength spikes of gamma rays. But to hear this full cosmic orchestra, we needed to build new ears. This required escaping the blanket of our own atmosphere, which acts as a protective but obstructive shield. For visible light, our atmosphere is reasonably transparent, which is why optical astronomy flourished first. But for other wavelengths, it's a nearly impenetrable barrier. Ultraviolet, X-ray, and gamma radiation are almost completely blocked, protecting life on Earth but rendering these cosmic messengers invisible to ground-based observers. Infrared light is heavily absorbed by water vapor and other molecules in the air. Even radio waves can be distorted and reflected. This is the primary reason we launch telescopes into space. By placing an observatory above the atmosphere, we remove the veil, allowing it to see the universe in all its fiery, energetic glory, free from the shimmering and filtering effects of our air. The Hubble Space Telescope, for all its fame as an optical telescope, also sees in ultraviolet light, a part of the spectrum completely inaccessible from the ground. But Hubble's view, as revolutionary as it was still just a portion of the conversation. To truly listen in, we had to build specialists. The Chandra X-ray Observatory, for example, is designed to see the universe in a state of extreme violence. Its mirrors are nearly parallel to the incoming light because X-rays would penetrate or be absorbed by standard telescope mirrors. They must be gently guided, almost like skipping a stone across a pond, to be focused onto a detector. Through Chandra's eyes, we don't see the serene, majestic whirl of galaxies. We see the superheated million-degree gas halos that envelop entire galaxy clusters, and the frenetic, high-energy dance of matter just before it vanishes into a black hole. Similarly, the Spitzer Space Telescope was our master of the infrared, able to peer through thick, opaque clouds of cosmic dust to witness the birth of stars hidden from optical view. And the Fermi Gamma Ray Space Telescope monitors the sky for the most powerful explosion since the Big Bang. The gamma ray bursts that signal the death of massive stars or the collision of neutron stars. Each of these windows reveals a different chapter of the same story. A dark, cold cloud of gas might be invisible to Hubble, but it glows with the heat of infant stars in Spitzer's infrared view. A seemingly quiet patch of sky in an optical image might be a brilliant, flashing beacon to Fermi, revealing a distant cataclysm. By combining these views, we move from looking at a photograph to experiencing a multi-dimensional portrait. We learn not just what something looks like, but what it's made of, how hot it is, how it's moving, and what violent processes are shaping its evolution. Our understanding is no longer passive. It becomes an active interrogation of the cosmos across the entire spectrum of light. And just as we were mastering this electromagnetic symphony, a revolutionary new sense opened up entirely, one that doesn't rely on light at all. On September 14, 2015, a new chapter in astronomy began, not with a flash of light in the sky, but with a subtle tremor in the fabric of space-time itself. The Laser Interferometer Gravitational Wave Observatory, or LIGO, detected the ripples produced by the collision of two black holes over 1 billion light-years away. This was the dawn of gravitational wave astronomy, a way of seeing the universe that is fundamentally different from any that came before. Gravitational waves are not made of photons. They are literal ripples in the fabric of space-time, distortions that stretch and squeeze space itself as they pass through. Where light can be blocked, absorbed, or scattered by dust and gas, gravitational waves pass through almost everything unimpeded. They offer a clear, direct view of the most violent and energetic events in the universe. This new sense allows us to probe regions that were previously completely opaque. The chaotic, furious merger of two neutron stars, for instance, is shrouded in an incredibly dense, hot maelstrom of matter and energy that would trap any light trying to escape. But the gravitational waves generated by this cosmic crash travel right out, carrying with them a pure signal of the event's dynamics, the masses of the objects, their spins, and the precise moment of their collision. The first detection of a neutron star merger by LIGO and its European counterpart, Virgo, was accompanied by a flash of light observed by telescopes across the electromagnetic spectrum, an event known as a kilonova. This marked the first time an astronomical event was observed in both light and gravitational waves, inaugurating the era of multi-messenger astronomy. It was like being able to see a thunderclap and hear the lightning bolt at the same time, providing a complete picture that neither messenger could offer alone. The future promises even more exotic ways of listening to the cosmos. Projects are underway to detect gravitational waves using pulsars, the rapidly spinning corpses of dead stars that act as cosmic lighthouses. By monitoring the precise timing of these pulses across our galaxy, astronomers hope to detect the background hum of gravitational waves from supermassive black hole binaries throughout the universe. And looking further ahead, a proposed space-based observatory called LISA would be sensitive to lower frequency waves, allowing us to hear the mergers of supermassive black holes at the hearts of galaxies, events that have been occurring since the cosmos was young. Every technological leap, from grinding a better lens to building a gravitational wave detector, fundamentally alters our cosmic perspective. Our view of the universe is not static. It is a narrative that evolves in lockstep with our ingenuity. Each new window we open corrects our vision, challenges our assumptions, and reveals a cosmos that is stranger, more violent, and more wonderful than we ever could have imagined. The universe has been broadcasting its story for 14 billion years, and we are only now, with our growing suite of technological senses, beginning to truly listen. Yet, all these technological extensions of our vision, from radio dishes to gravitational wave detectors, share a fundamental starting point: the human brain. Every image, every data stream, every interpretation of the cosmos is ultimately filtered through the lens of our own unique perception and cognition. We are not passive, objective recorders of the universe. We are active interpreters, and the very way our senses and minds are built profoundly shapes the story we tell about the cosmos. This becomes strikingly clear when we consider the breathtaking images that define modern astronomy. The iconic pillars of creation from the Hubble Space Telescope, with their majestic, ethereal glow, or the fiery, detailed landscapes of nebulae from the James Webb Space Telescope, are not direct snapshots as our eyes would see them. They are translations. Our eyes are exquisitely tuned to a very specific range of wavelengths, what we call visible light, because that is the band of radiation most abundantly emitted by our sun. But the universe communicates across the entire electromagnetic spectrum, and most of that conversation is silent to our biological eyes. To hear this full conversation, astronomers assign colors to invisible light. An image from the Chandra X-ray Observatory, which sees the universe in incredibly high energy radiation, might map X-rays to the color blue. data from the Spitzer Space Telescope observing in the infrared might be represented as red. When these different data sets are layered together, we create a composite image that is both scientifically rich and visually stunning. This process, known as representative color or false color imaging, is not about deceiving the public. It is about making the invisible visible and understandable. It allows us to see the relationship between different physical processes happening in the same region of space. In a single image of a supernova remnant, we can see the blast wave in X-ray blue, the expanding shell of shocked gas in optical green, and the cooler dust in infrared red. These images are a form of data visualization, a bridge between the raw numbers collected by our instruments and the powerful pattern recognizing capabilities of our brain. They transform abstract measurements into a form we can intuitively grasp, revealing the complex multi-wavelength anatomy of cosmic objects. This leads us to another deep-seated feature of human cognition, our relentless drive to find patterns. Our brains are magnificent pattern detection engines honed by evolution to recognize faces in the clouds, predict the changing seasons, and identify the subtle signs of prey or predator. This skill was essential for survival, but when we turn it to the cosmos, it takes on a new dimension. It is this very tendency that allowed ancient cultures to connect the dots of bright stars into constellations, weaving elaborate myths and narratives across the night sky. We look at the scattered distribution of thousands of galaxies in a deep field image, and our minds immediately try to impose order, to see filaments and walls and voids, to trace the large-scale structure of the cosmic web. This isn't just a poetic impulse, it is the foundation of scientific discovery. Recognizing a pattern is the first step toward formulating a hypothesis about the underlying rules that created it. This pattern-seeking nature is a double-edged sword. It is what allows us to deduce the laws of physics from the rhythmic motions of the planets, but it can also lead us astray, a phenomenon known as pareidolia. This is the tendency to perceive familiar patterns like faces or animals in random or ambiguous stimuli. We see a face on Mars or a cosmic hand in a nebula. While these are fun curiosities, they remind us that our interpretations are not always a direct reflection of reality. They are a collaboration between the data coming in and the pre-existing templates in our mind. The challenge for science is to use our pattern-seeking abilities judiciously, to distinguish between meaningful cosmic signals and the random noise that our brains are so eager to organize into something familiar. This constant interplay between observation and interpretation is the heart of the scientific process. We collect data with our advanced tools, our brains search for patterns within that data. We construct models to explain those patterns, and then we go back and collect more data to test our models in a continuous cycle of refining our understanding. The universe we describe is always, in some profound way, a universe seen through human eyes and understood by a human mind, a unique perspective on a cosmos that is vastly stranger than our senses alone could ever perceive. Yet, for all the breathtaking progress we have made in mapping the cosmos and deciphering its history, we must stand in humble awe before the vast expanse of our own ignorance. The very discoveries that have defined modern cosmology have also illuminated profound mysteries, questions so deep that they currently define the absolute frontier of our understanding. The universe, it seems, is content to reveal its workings one layer at a time, and the deeper we probe, the more enigmatic the underlying reality appears. The most glaring of these mysteries is the true nature of the universe's two dominant components, dark matter and dark energy. We have mapped their gravitational influence with exquisite precision. We know they constitute 95% of the cosmos, and yet we have no idea what they actually are. Dark matter remains a ghost. We see its shadow in the way galaxies spin, and in the way light bends around galaxy clusters, but decades of searching have failed to directly detect a single particle of it. Deep underground laboratories wait for a hypothetical WIMP to bump into a nucleus. Powerful particle colliders like the Large Hadron Collider try to create them in high-energy collisions. So far, the detectors remain silent. The possibility remains that dark matter is not a single type of particle but a family, or that it interacts with our world through forces even weaker than we've imagined. Every null result, while frustrating, forces us to rethink our assumptions and broadens the search, reminding us that the majority of the universe's matter is a substance completely alien to everything we are made of. Dark energy is, if anything, even more perplexing. It is not a substance but an effect, a property of empty space that causes the universe's expansion to accelerate. When we try to calculate the expected energy of the vacuum from quantum physics, the number we get is wrong by a factor of 10 to the power of 120. That is not a small error. It is the largest discrepancy between theory and observation in the entire history of science. This monumental failure tells us that we are fundamentally missing something crucial about the nature of space itself. Is dark energy truly constant, as Einstein's cosmological constant suggests? Or could it be evolving over time, perhaps a field that is slowly decaying or strengthening, which would lead to a radically different future for the cosmos? Answering this question is not just about completing a model, it is about determining the ultimate fate of everything. Pushing back to the very beginning, we confront the mystery of the Big Bang itself. While the theory beautifully explains the expansion, the cosmic microwave background, and the abundance of light elements, it is silent on the question of what caused it. What was the initial condition? What, if anything, came before? The equations of general relativity break down at the moment of the singularity, a point of infinite density and temperature where the laws of physics as we know them cease to have meaning. This is not a physical answer, it is a sign that our theory is incomplete. The theory of cosmic inflation offers a compelling description of the universe's first fraction of a second, stretching a quantum seed to cosmic size, but it too does not explain the ultimate origin. What ignited the inflattened field? Did the universe emerge from a previous cosmic cycle in a big bounce, or from a quantum fluctuation in a deeper void? These are questions that currently lie at the very boundary between physics and philosophy. This failure at the beginning points to what is perhaps the most profound theoretical challenge in all of physics, the problem of quantum gravity. We have two magnificent and supremely successful theories: quantum mechanics, which governs the very small, and general relativity, which describes the very large. Yet they are fundamentally incompatible. When we try to apply the probabilistic, fuzzy rules of quantum mechanics to the smooth, geometric fabric of spacetime described by general relativity, the mathematics produces nonsensical infinities. This conflict only becomes critical in extreme environments, the center of black holes and the first moment of the Big Bang, where immense gravity acts on a microscopic scale. Unifying these two pillars of modern physics is the holy grail of theoretical physics. String theory, which proposes that fundamental particles are tiny vibrating strings, and loop quantum gravity, which suggests spacetime is woven from discrete loops, are two ambitious attempts. But without any experimental evidence to guide us, the path forward remains murky. A successful theory of quantum gravity would not just complete our picture of the universe, it would revolutionize our understanding of reality itself, telling us what space and time truly are at the most fundamental level. Beyond these grand questions lie other, equally puzzling enigmas. Why is there such an overwhelming predominance of matter over antimatter? The laws of physics, as far as we can tell, are almost perfectly symmetric between particles and antiparticles. Yet, for us to exist, there must have been a violation of this symmetry in the early universe, a 1 in a billion imbalance that allowed a tiny surplus of matter to survive the mutual annihilation. We have found small violations of these symmetries in particle physics experiments, but they are far too feeble to account for the universe we see. something else, some new particle or interaction operating at fantastically high energies in the first moments, must have tipped the scales in our favor. Finding that mechanism is a central goal of particle physics, and then there is the puzzle of our own existence. The fundamental constants of nature, the strength of gravity, the mass of the electron, the force that holds atomic nuclei together, all seem to be fine-tuned with incredible precision to allow for a universe that can support complex structures and life. If any of these numbers were altered by even a tiny fraction, stars would not burn, elements would not form, and the cosmos would be a lifeless void. Is this staggering fine-tuning a cosmic coincidence, a result of our universe being one bubble in a vast multiverse where every possible set of constants is realized? Or does it point toward a deeper, yet undiscovered, principle that logically connects these values? These are not minor puzzles to be solved on the margins. They are the fundamental questions that define the future of cosmology. Each represents a chasm in our understanding, a frontier where known physics ends and the true adventure of discovery begins. The universe has been generous with its clues, but the greatest chapters of its story are still waiting to be read. While our current telescopes have painted a stunning portrait of the cosmos, the next chapter of cosmic discovery is already being written, with a new generation of observatories poised to peer deeper into the mysteries of dark energy, to listen for the faintest whispers of gravitational waves, and to potentially uncover phenomena we cannot yet even imagine. These are not merely incremental upgrades. They are instruments designed to answer the most profound questions we have about the universe's origin, composition, and ultimate fate. One of the most anticipated projects is the Vera C. Rubin Observatory, formerly known as the Large Synoptic Survey Telescope, now named for the pioneering astronomer who provided such crucial evidence for dark matter. This facility, perched atop a mountain in Chile, is not just a telescope, it is a cosmic census machine. Its primary instrument is the largest digital camera ever built for astronomy, a 3.2 gigapixel behemoth that will capture an area of sky equivalent to 40 full moons in a single exposure. Over a planned 10-year survey, it will scan the entire visible southern sky every few nights, creating an unprecedented motion picture of the cosmos. This relentless observation will catalog billions of galaxies and track the brightness of millions of stars, not as a static snapshot, but as a dynamic film. This will allow astronomers to detect incredibly subtle changes, like distant supernova flickering into view, asteroids moving through our solar system, and even the subtle distortions in the shapes of galaxies caused by the gravitational lensing of dark matter. By mapping the distribution and growth of cosmic structure with such immense detail, the Rubin Observatory will provide the most precise measurements yet of the influence of dark energy over the last several billion years, helping to determine if its strength is truly constant or if it evolves over time. But to probe the very first moments of existence, we need to listen to the universe in a completely different way. This is the goal of the Laser Interferometer Space Antenna, or LISA. While ground-based detectors like LIGO are sensitive to the high-frequency ripples from the mergers of stellar mass black holes, LISA will be a space-based observatory designed to detect gravitational waves at much lower frequencies. Imagine it as a giant triangle of 3 spacecraft flying in formation millions of miles apart, connected by laser beams. As a gravitational wave passes through this triangle, it will ever so slightly change the distance between the spacecraft, stretching and squeezing the space they occupy. LISA will be exquisitely sensitive to the colossal, slow-motion dances of supermassive black holes. When galaxies merge, their central black holes, weighing millions or even billions of times the mass of our Sun, will eventually spiral together, generating a gravitational wave signal that can last for years. By detecting these waves, LISA will essentially hear the universe's growth, tracing how the largest structures assembled over cosmic time. Even more remarkably, LISA may be able to detect the faint, primordial gravitational waves generated by cosmic inflation itself. This would be a direct echo from a time before the Big Bang's afterglow, a smoking gun for the theory of inflation and a probe of physics at energy scales far beyond anything achievable in a particle collider on Earth. Beyond these flagship missions, a suite of powerful new eyes will continue to expand our view across the electromagnetic spectrum. The Nancy Grace Roman Space Telescope, often seen as a wide-field companion to the deep but narrow view of the James Webb Space Telescope, will conduct vast surveys to study dark energy and hunt for exoplanets using a technique called microlensing. On the ground, the Extremely Large Telescope, or ELT, with a mirror nearly 40 meters in diameter, will gather so much light that it will be able to directly image rocky exoplanets and analyze their atmospheres for signs of biological activity, potentially answering the age-old question of whether we are alone in the universe. Meanwhile, new arrays of radio telescopes will map the distribution of neutral hydrogen from the earliest epochs of the universe, revealing the cosmic web as it was still forming. What is truly exciting is that the greatest discoveries from these instruments may not be the answers we expect, but the questions we haven't even thought to ask. Every time humanity has built a new window onto the cosmos, we have been confronted with the utterly unexpected. The discovery of the expansion of the universe, the cosmic microwave background, dark matter, and dark energy all came as profound surprises that fundamentally reshaped our understanding. The next generation of explorers, armed with these technological marvels, will undoubtedly stumble upon anomalies and phenomena that defy our current models. They might find evidence for entirely new particles that make up dark matter, or detect a signature in the gravitational wave background that points to a cyclic universe. They could discover that the laws of physics are not constant across the universe, or find a planetary atmosphere with a chemical imbalance that screams of life. The future of cosmology is not just about filling in the blanks of our existing theories. It is about writing entirely new chapters in the story of the universe, chapters whose first words are only now being formed in the minds of the scientists and engineers building the tools to see the unseen. This incredible journey from the quantum foam to the cosmic web inevitably brings us to a moment of profound reflection. We have mapped the universe on scales so vast they defy human intuition, and we have probed its origins back to a time before time itself had meaning. But what does this grand cosmic story, this explanation for why the universe looks the way it does, ultimately mean for us? It bestows upon us a unique and powerful gift, a cosmic perspective that reshapes our understanding of our own place in the grand scheme of things. To grasp that our home planet is not just a world, but a tiny, fragile oasis orbiting an average star, which is itself one of hundreds of billions in a galaxy that is, in turn, just one of trillions, is to experience a deep and humbling awe. The daily concerns and conflicts that can seem so all-consuming are, from this vantage point, taking place on a microscopic stage in an immeasurable arena. This perspective is not meant to diminish our existence, but rather to ennoble it. The same physical laws that govern the spin of a galaxy also dictate the orbit of our planet around the Sun. The carbon atoms that form the backbone of our DNA were forged in the heart of a long-dead star. The oxygen we breathe was released into the cosmos in a supernova explosion that occurred billions of years ago. We are not merely inhabitants of the universe, we are a product of it, a conscious expression of the cosmos becoming aware of itself. This connection transforms the universe from a distant, abstract spectacle into a story of which we are an intimate part. Our quest to understand the cosmos is, in a very real sense, the universe beginning to understand its own origins, structure, and beauty. This journey also instills a sense of profound responsibility. As far as we currently know, our pale blue dot is unique in its ability to harbor life. In all our searching, we have found no other world with forests and oceans, no other signal of intelligence beyond our own. This isolation underscores the incredible preciousness of our world and the life it supports. The story of the universe tells us that the conditions for our existence are the result of an immensely long and delicate chain of cosmic events. It highlights that our planet is not a disposable resource, but an exceptional and likely rare haven in the vast, cold emptiness of space. The cosmic perspective, therefore, is not just an intellectual exercise. It is a call to stewardship, urging us to protect the fragile world that has given us the chance to look up and wonder. Ultimately, the question of why the universe looks the way it does is more than a scientific inquiry. It is a deeply human one. It speaks to our innate curiosity, our desire to find our place in a larger narrative, and our need to connect with something greater than ourselves. Every time an astronomer points a telescope at a distant galaxy, or a physicist analyzes data from a particle collider, they are participating in this ancient, ongoing conversation. They are adding another verse to the epic poem of existence, a story that began with a flash of light nearly 14 billion years ago and continues to unfold within us. The universe's appearance is not a static picture. It is a dynamic, evolving narrative, and we, for a brief and brilliant moment, have the privilege of being both its audience and its scribes, tasked with reading the story written in the stars and adding our own small but meaningful chapter. So, after this incredible journey across space and time, what is the final answer to our question? Why does the universe look like this? The majestic spirals of galaxies, the delicate glow of nebulae, the vast cosmic web, these are not random decorations. They are the direct and inevitable consequence of a handful of fundamental laws, playing out over an almost unimaginable span of nearly 14 billion years. The universe looks the way it does because of the relentless pull of gravity, sculpting dark matter into an invisible scaffold. It looks this way because of the strange, repulsive push of dark energy, now dictating the pace of expansion on the largest scales. Its appearance is a fossil record, a history book written in light, telling the story of quantum fluctuations stretched to cosmic proportions, of the first stars that ignited to end the dark ages, and of generations of stellar life and death that forged the very elements we are made of. And crucially, the universe looks this way to us because of our own particular viewpoint, limited to the sphere of light that has had time to reach us, and interpreted through the ever-advancing tools we build to extend our senses. The cosmos we perceive is a specific portrait, one frame from a much longer film, seen through a particular set of lenses. This quest to understand the cosmic landscape is far from over. In fact, every answer we uncover seems to open up new, even deeper questions. The nature of dark matter and dark energy remains one of the greatest puzzles in all of science. The search for a theory of quantum gravity, which would unite the very large with the very small, continues to push the boundaries of human thought. The ultimate origin of the Big Bang and the possibility of a multiverse beckon from the very frontiers of knowledge. What we have learned is not a final conclusion, but a chapter in an ongoing story of discovery. Each new telescope, each new experiment is like turning a page, revealing surprises that challenge our assumptions and force us to rethink our place in the grand scheme. The universe is not a static picture to be solved, but a dynamic, evolving narrative that we are only just beginning to read, and that is where you come in. This story does not belong solely to scientists in isolated laboratories. It is a fundamental part of the human experience. This innate curiosity, this drive to look up at the night sky and ask why, is what connects us to every human who has ever gazed upon the stars. So the next time you find yourself under a clear, dark sky, take a moment, look up. Let your eyes adjust to the faint glow of the Milky Way, our home galaxy, arching overhead. Find a fuzzy patch that might be the Andromeda Galaxy, a trillion stars shining with light that began its journey to you before humans walked the Earth. In that moment, you are not just a passive observer, you are a participant in this grand cosmic inquiry. You are the universe looking back at itself, contemplating its own origins and its own nature. The greatest discoveries often begin with a simple act of wonder, so stay curious, keep looking up, and share that sense of awe. Tell us in the comments what part of this cosmic story fascinates you the most, or what question about the universe keeps you wondering. The conversation is just beginning.